So I guess we are ready to start the second series of talks by Professor Dr. Volker Marker. He's the chair of database systems, the Database Systems and Information Management Group at TU Berlin, director also of the Berlin Institute for the Foundation Learning Data, BIFOLD, and chief scientist and head of the Intelligent Analytics for Massive Data Research Group at the German Research Center for AI, the FKI. And today he will present, of course, very well known in the scalable database work, also for his contribution to the open source work with Stratosphere and Apache Flink. And nowadays, he's working on another great project, NebulaStream, for massively distributed data stream processing on the edge in heterogeneous volatile environments. And we are very excited to hear his talk. And it will be followed by a hands-on session by Yannick, who came with Professor Volker. And Volker, the floor is yours.
Thank you, Dimitris, for the nice introduction. I'm very happy to be here today. And first, before we start, though, what to expect. And this is a discussion that I often talk to. I used to talk about like that with my grandmother, but also when you talk to politicians, when you explain what you're doing, because it may be sometimes useful if we talk about systems. Because what I explain then is, and actually I had explained it like that to Angela Merkel at some point of time, and she really understood. Because what are we really doing, right? So we are, when you think about water, you can do really beautiful things with water. You can cook Michelin chef meals, you can make wonderful wine, you can make beautiful gardens. So we do nothing of that. I just say I'm a plumber. And what does that mean? Plumber means you're worrying about the pipes. You're worrying about the pipes that put the water at the right place, right? And also, there's lots of things about plumbing that is really important. So you have to worry about water pressure. You have to worry about wells. You have to worry about pumps. You have to worry about potentially water treatment. If you're in scarce areas, water desalination, lots of technology. And the interesting thing is, without that, you would not have any gardens, you wouldn't have any wine, you wouldn't have any Michelin meals. So that stuff is really crucial, really important. And actually, also, it's an infrastructure, there's a lot of money to be had in that, which is really relevant for industry. So it's a very important thing that we are doing. The only difference is we are not doing this for water, we are doing this for data. And with that, I just want to kickstart that because we've heard a lot about, or you have heard already before about, of course, machine learning and AI. And the view that I think we all can accept is that big data and machine learning are really the two key drivers of innovation and in AI and in data science, right? So it's really those two disciplines with, you know, having enough data that you have to manage and process to train those large models, which nowadays, of course, we talk about LLMs, we talk about deep networks, we talk about transformer architectures and so on, right? But in the end, it's really those two, and those two belong together. And this is also important to point out because sometimes one might get the impression it's all about machine learning algorithms or so on, but it's really a lot of it is about data. And this really has a profound impact on the sciences and the humanities on the one hand, and on industry on the other hand. And if we talk about the sciences, then we usually talk about what the late Turing Award winner Jim Gray has dubbed the fourth paradigm, which is, you know, analyzing massive amount of sensor data, and that includes, you know, here the example on the top of this picture is a Large Hadron Collider, and I'm sure many of you have heard about, you know, that essentially through statistical methods based on large data analysis, scientists were able to confirm the existence of the Higgs boson, right? So fascinating scientific achievement, but this is really a different paradigm, and I talk a bit more about that. Below you see the square kilometer array, which is now in astronomy, you know, a huge, essentially, a telescope that is combined out of many different telescopes, and that proves a lot of data that has to be analyzed. In industry, we talk about data to be a new factor of production. And so you see some examples here in smart manufacturing or a paper mill that have lots of instrumentation. So the important thing there, though, is, and you may have heard this when people talked about data or big data, the Gartners of the world, they always said data is the new oil or data is the new gold, and I totally disagree. I think this is absolutely not true, because data is not a resource. Gold and oil are resources. Instead, data is a factor of production. And if you look at economic theory, factors of production, does any of you know the factors of production in economic theory? Anybody studied some parts of economics? Yes, please. Mm-hmm. Capital, yeah, exactly. So it's labor, the natural resources, which usually is like people also subsume it often as soil, the soil out of which you grow stuff, and there's capital. And I always say in this context, because data is it's not a resource, because a resource, once you use it, it's gone, right? So oil you use in production, it's gone. Data, when you use it, it's not gone, so it's there, right? So that's similar to an analogy to soil, and I'll give you an example of it later. So data is not the new oil, data is the new soil, and we'll talk about that in a second. But first, let's talk about the fourth paradigm. So the fourth paradigm, essentially a new standard for research, because if you look back thousands of years ago, Socrates, Aristoteles, there was empirical research, which was describing natural phenomena, and then you find the elements are fire, earth, air, and water, right? Then over the last centuries, we had theory building sciences, which is really about modeling and generalizations. So think of Newton sitting in the garden, the apple falls down from the tree, one comes up with the idea, and of course tests it experimentally and comes up with a model for force equals mass times acceleration. And in the context of that, you even realize there's this concept of gravity. So this is theory building. Then over the last decades, we had computational sciences, which essentially were characterized by supercomputers and large complex simulation systems, which were usually informed by large differential equations, and you do things like weather prediction, earthquake prediction, fluid dynamics, climate research. That's all going with large simulation models. And of course, those three types of sciences still exist, but there's a fourth one that has emerged and has become more crucial in the last 20 years and has also led to a bit of a breakthrough, and that's this data-intensive science, and the Large Hadron Collider Higgs boson example is one example of that. And we see more and more of that in the digital humanities, in many, many fields, right? So it's really about massive amounts of data that are generated by some form of sensors, oftentimes so much data that you couldn't even store it when it's being generated in some of those experiments. So you have to throw away data, and you have to make sure that you only save the right amount of data, and you have to do the generation process with specialized hardware. So it's totally extreme things. And this is the fourth paradigm. At the same time, in the economy, data is a new factor of production. And here I have the analogy with, soil. So when you have soil, you have to prepare the soil to dig it in order to be able to plant. And then you fertilize it, then the plant will grow, and eventually you can harvest. For data, you can think of it as a similar flow. So the data, you extract information, you integrate it, you analyze it, and you use it. And then with that, you actually get the same data and new data, and you can use it again, right? So it's a factor of production. Okay, now what is the role of data management systems in this context? So this is just to give an idea of the field that informs and why I'm doing the work that I'm doing. But this is, I would say, a general description of what we are doing in data management systems. So you have this data analysis or data science process, data analysis workflow, which consists of the steps of first extracting the information, integrating it, analyzing it, building some models, and deploying it. And usually this is iterative, so that is after building the model, you may actually go back and refine it. And the important thing is, this is what I in particular explain my machine learning colleagues also, is the difference between machine learning and data systems, data management here is we are thinking of this as a process, not of a project. So if you have worked with colleagues in machine learning, you may have noticed often they think of that as a project. So what's the difference between a process and a project? Can anybody explain that to me? Any thoughts? Yes, please.
The project can finish.
Very good. A project finishes, and the process is something that's made to be repeated, maybe even forever, but continuously, but it's not just for one-time use. And that, of course, makes a difference. Because if I design a data analysis workflow, a machine learning workflow, in order to do a project, like my colleagues in machine learning, they do quantum chemistry and they want to do some experiments and they analyze things, and after that, things are thrown away, right? So you design your entire workflow very differently. But the idea of data management is always to look at this as a process, which is repetitive. And if you do that, that requires quite some different things than if you make this a process. So what does that mean? So if we look at this as a process, and if we want to execute this process on massive heterogeneous data sets and data streams, which is essentially what people call big data, right? So velocity, which means It's streams, massive, meaning it's volume, heterogeneous, which means it's there's this variety, if you heard about those V's, right? Then there's two aspects. The first aspect is that there is a machine learning expert, data scientist, data analyst, call this person however you want, that has to specify this process. And if we want to run it on those large architectures, the specification has to be processed efficiently on big computing infrastructure, right? So those are the two aspects of what we do with this process. And there is two challenges. The first challenge is the human efficiency. So we have to relieve this machine learning expert from, really dealing too much with the hardware, because otherwise it won't scale, in the sense that it will take too long to write those programs. It will be, you will not have enough trained people that can do that. So you need to have a specification that allows for that. And the boilerplate answer in data management, data systems, here always has been declarative programming languages, right? So what is a declarative programming language? What do you do in a declarative programming language versus an imperative or functional programming language? Yes, please.
Because defining procedures, you just write the name of what you want.
So you specify what you want. You do not specify how you compute this. So this is kind of the principal idea of declarative programming languages. And of course, this is a very vague definition, because what's declarative for one person is, very detailed for another, right? So you can always debate, is it declarative or not? But in this case, the goal is declarative in the sense of abstracting from the underlying execution, abstracting from the underlying hardware, and in this way being able to focus on the problem domain. So that's declarative languages. If we now talk about typical things that we do in data management to address that, is we build algebraic and statistical processing models, which give you alternative executions with different physical implementations of operators. And you know this probably from relational databases, right? So you have a query optimizer that's automatic optimization based on a model. In this case, usually it's relational algebra. And if you have relational algebra, you have properties like associativity, commutativity, and distributivity of operations, which allows you to do optimizations like pushing selections down so that it's efficient, or pushing projections down, or choosing the right join order because of the, also again, commutativity and distributivity of the Cartesian product or join operation, those kinds of things. And you have those statistical models that help you to trade off which of those is the best implementation. And then you have physical operations that efficiently implement that. So this is essentially the human efficiency, somehow declarative languages. And if we talk about technical efficiency, the challenge always is the memory hierarchy. So it's always about, we have a slower, bigger level in the memory hierarchy and a faster, smaller one. And that could be in memory with caches. It could be between cache and disk. It can be many different things, right? So we always have to look into that. And the usual answer to deal with that is efficient data structures, algorithms. We want to parallelize, we distribute, and we may also use some form of pre-computation or indexing in order to have efficient direct access. So, and the goal of the data management systems research then is in this overall framework to scale this data analysis process, both with respect to the human and the technical efficiency. So this is in essence the goal that we are striving to do, I would say, as a field as a whole. And I will give you some examples. I will spare you the details, but some examples of this would be applications in the sciences like remote sensing, where we analyze massive satellite data archives in order to analyze trends like deforestation, or it could be in smart production, like having paper mills where you have many different sensors, and you want to determine based on that, will the paper tear in a paper machine, right? So those would be kind of examples, and we've looked at those kind of examples. But I now want to go into a bit more technical aspects and talk in this stage of what I have been doing in the past in a system that I've created with my team that was called Apache Flink. And I will do that because we are building a new system that you will learn much more about afterwards, NebulaStream, which is a massively distributed data processing system in its vision. But I'll start with Apache Flink because this informs why we are building this new system, and I can also explain what's different. So first, the background, and also because it's an interesting success story. So in 2008, I started a research project called Stratosphere, and this project, so this was, I was in 2006 when I was working still at IBM, I was probably one of the first users of a system called Hadoop that was informed by the MapReduce programming model that was created by Dean and Genovat, right, from Google, or proposed or conceived. So who knows Hadoop or MapReduce here? Yeah, so a good amount of people. So what's the key concept of Hadoop or MapReduce? Can anybody tell me? Iteration. Not really iteration. No. Yes. Yeah. So interestingly, so the idea was because map and reduce are not new, right? But what's map and reduce? Map and reduce are two second-order functions. You have those in any functional programming language. Think Scala, think ML, think your favorite function programming. You have those functions, and those functions are two functions that can do a computation over collections, which is what usually we want to do in data management, right? We do computations over collections, and what a map does, a map is a second-order function that takes a first-order function f and applies this to each element of the collection independently. So an example would be, we have a map, the function could be times 2, multiplying a number times 2, and the collection could be the numbers 1, 2, 3. So the output of map times 2, 1, 2, 3 would be 2, 4, 6, right? It's 3 items, each of them multiplied by 2. So, and the beauty of why this is so useful is because you can do this computation independently for each of those different functions, data items, right? So you get a data parallelism that essentially depends on the number of items in your collection or the number of processors, whichever is the smaller number, right? So this is the map function. And then what the guys at Google also conceived this, if we want to make this a parallel programming model, then we also need a second function. And the idea was really to use this, and this is maybe see where I said iteration, because the idea was to do this for one iteration of the PageRank algorithm. This is really what this was conceived for. And so the second function is the function called reduce. So in reduce in the functional programming world is a function that, again, it's a second order function. It takes a collection as input. And in this case, it computes, it applies the function to all of that input and produces one output. So that means reduce with the function plus with the input 1, 2, 3, the output would be the number 6, right? So this is the reduce function, a second function in functional programming, second order function. And the interesting observation now is that, of course, this function reduce is not a very good function to parallelize the way I just have described it, because of course you could, if the function is commutative and associative, you could play some tricks like building aggregation trees or whatnot in order to parallelize this aggregate, but still you don't get a good degree of parallelism. But the idea that then Dean and Genowat had, let's introduce a different kind of data model, which we call a key value data model. And that means instead of doing a reduce for all the numbers, we first do a reduce, which is a grouping by keys. So that, and for each of those values that have the same keys, we produce the aggregation, or we apply this first order function. That's the argument, right? So that's really why you need the key value model. You need it for reduce function. And in this way, it's a parallel programming where you actually, the number of computers then you can use in parallel is the number of distinct keys, right? Which if you have a good amount of distinct keys, you can get some good parallel processing efficiency. So that was the idea. And this was really very popular in 2006, 2007. And then people started this, what they call NoSQL movement, right? Which is instead of relational algebra, trying to program a lot of things and kind of trying to build things like relational processing with MapReduce, which in my opinion was a really, really bad idea. So I mean, Jeff Allman, they wrote a lot of papers out of Stanford about, using MapReduce to implement joins, which is, and I was really shocked. I found this really horrible. And the reason why I found this horrible is because it doesn't make sense. It makes sense if you are Jeff Allman who likes compilers, right? So it makes a lot of sense, of course, but it doesn't make sense if you want to abstract, if you want to have a declarative programming like we just talked about, where you want to actually relieve the programmer from the systems aspect. Because how would you do a join in MapReduce? There are lots of people that discuss tricks like map side joins, reduce side joins, you take the inputs. And the fundamental problem there is you cannot do it because you only have one input, right? And the join requires 2 inputs. So you cannot do it unless you do some really strange tricks, which means that you're putting some logic into the first order function, like you're implementing a join algorithm in the first order function. Or even worse, if you're doing joins across multiple ones, you probably even implement a query optimizer in your first order functions, and you definitely don't want to do that, right? So, so this is why, to me, the system was totally broken. Now, it works well for what it was originally designed for, which is ETL and, essentially running one iteration of a of a PageRank computation. But this generalization to me was a dead end. At the same time, it was very powerful and great, and it had a couple of really great properties. So the first great properties was this big scalability, meaning you can scale out to commodity hardware, to thousands of nodes, which is something that database systems then couldn't really do. And they were not designed for that. You had some parallel databases that could run in, in fiat nothing mode, but they were all designed for short-running transactions. And that means if a failure happened during a transaction, the only thing you could do is to restart it. That doesn't work if you want to compute paging on the internet, right? You cannot restart because there's always failures happening if you scale out far and if you have long-running computations. So that means in order to scale, they looked at fault tolerance and a couple of ways, storing records in checkpoints in the distributed file system, redundancy, doing redundant speculative execution, a couple of really cool things. And at the same time, because it was a second-order functional programming model, it employed user-defined functions, meaning that you did not have to define the database schema, because that's one of the fundamental problems of relational databases is that you need a relational schema, right? And lots of people don't think about a relational schema in the get-go where they want to refine it, and in particular when you have big data. And with Hadoop, you had this opportunity to create a schema while you're reading the data, so schema on read. It was very attractive in this big data time. So those were really good things about MapReduce, right? But and so what I thought back then was, could we not build a system that takes the best of both worlds, that takes from the database technology those things that we all love and like, which is a principled foundation with an algebra that you can optimize, right? So you have declarativity to a certain degree. You have a query optimizer, and more importantly, also you have robust out-of-core execution, which means if your data doesn't fit into memory, which is a problem also in MapReduce, if you cannot partition it properly, then and the data doesn't fit into memory, then you will get into serious problems with thrashing. So avoiding that by having robust out-of-core algorithms like two-phase multiple merge sort or hybrid hash joins, Grace hash joins in the distributed setting, right? Those kinds of algorithms that we all know one should have. But in this world, and in addition, one observation was the world is changing. That was my belief then in 2008. And we need two more things that none of the systems had, although the system that at the same time came about, Spark, also didn't really have it. That was iterations. And okay, we thought, well, we should have more advanced data flows, more general APIs. But the two really key things were iterations and streaming. And iterations, I mean, so in MapReduce, you could do an iteration by running an outside program that runs a MapReduce program, and it would be an external driver, right, like a shell script. And in this way, you could do multiple iterations. But the system itself wouldn't know that it does iterations. And similarly, by the way, in a system that was happening at roughly the same time when we built back then Stratosphere, later Flink, there was a system called Spark that also couldn't do iterations because that was written in Scala, and you could parallelize what is an iteration. Maybe to step back, an iteration is a function f that is executed inside a while statement or a loop statement, right? A for statement. So that means, and this function f would be parallelized. But the system that runs the outer driver, the loop, wouldn't know that it runs a loop. And there's a couple of things that you can do if you know that you're running a loop that make it much more efficient. You can optimize in a very different way. We did lots of work on that. I'm not talking about that today. But that was one of the key things that we said. And we need iterations because any non-trivial data analysis method is iterative in nature. Think of K-means clustering. Think of many machine learning algorithms. They are iterative in nature. That's why I felt we need to do iterations. And the other thing we said, okay, and more data is generated in the cloud. And you want to analyze it directly in the cloud in more or less real time. So you want to support native streaming data. And the problem with systems like Hadoop or also to some degree Spark are that they are either batched, or if they do streaming, they call it micro-batched, which is you're taking a smaller batch and you're executing the smaller batch. And we said you need to do native streaming. And native streaming means, on the one hand, you have to support in a stream, there's one thing we don't like, which is order, right? Because in data management, if you have order presents challenges. Why does order present challenges? Any thoughts? Why is order difficult for data processing?
It's blocking.
Order, if you have to sort, it blocks. But the other, that's one problem if you really need to fully sort things. But the other thing is, if you have order and you need to preserve the order, it's just the order that comes in, then the challenge is, you may not be able to parallelize that, right? Because you have to process one before the other, right? And the beauty is if something is a set, I can just scale it out, right? So if my collection is ordered as opposed to unordered, it makes a difference. you can play tricks like with watermarking and things like that. That's what people do in streaming in order to sort of create some kind of partial orders or orders within the bounds, essentially, right? That's what one does in order to remain efficient. But that's what one has to do. One has to worry about order. And the other thing one has to worry about is, because a data stream is potentially infinite,
pipeline
queries don't make sense. You cannot really ask too many meaningful queries, because the only thing you can do is a query on a record. But otherwise, if you want, a join is not meaningful on two streams, right? So the only thing you can do is you could, in theory, join one stream with some bounded data set, but joining a stream with another stream per se is not an operation that you could well define, because both are infinite. So the only way, and the way around that, and for many other things, also for summing up something or so, it doesn't make a lot of sense. But the way to do this semantically meaningful is we have to discretize the stream. Discretization means the most common example would be what people call a window. So you put a window over a stream, and then for a window, now you can do all those things again, because I'm saying I'm looking at the last 100 records, and I'm joining the last 100 records from this stream with the last 50 records of the other stream. That's meaningful again. And you can, windows, this would be an example of account-based. It can also be time-based windows, which is the last 20 minutes of that stream versus the last 10 minutes of that stream. But there could be much more complex windows. That could be, for instance, windows that the number of people in this room could be a window, right? And that means the most general way of specifying a window is I have so a window is essentially some stored data set that occurs during the stream, and you have, when something comes in the stream, you admit it to the window. So you need an admission policy or an admission function that decides should this go into the window or not. And at some point of time, you may want to remove something from a window again or close that window, right? And then there's some time when you want to trigger a computation from a window. So those are kind of three functions, right, that you want to do. So this is the things that you have to think about when you do streaming. And so that's what we said, let's build a system that can do that stuff. And over time, we actually, that started with two of my PhD students at TU Berlin, and later on some other students at TU Berlin, and then other university groups, including Joanna's group in INRIA, joined in, and it helped us to build a major system that in the end became open source, which is Apache Flink. So we had to change the name. I'll tell you, if you're interested in offline, why we had to change the name after that in the break or in the evening. But so Flink, right, it's not Stratosphere. Apache Flink is an open source stream processing framework for distributed, high-performing, always available and accurate data streaming applications. So that means it can support both bounded and unbounded data. Bounded is, you can think of it like batch data or data at rest. Unbounded data is now streaming data or data in motion. And as I said already, you need event time semantics. That's important when things are streaming. And you need to worry about state. State is essentially, when you deal with iterations, the thing that is inside the loop, this function that you're executing inside the loop, it changes something on your big data. And the next time I go into the loop, I need to have this changed state. And state is a problem because state, you have to manage it. In particular, if it's big state and it's distributed and you're running on a cluster, it has to be fault tolerant. This is an issue, right? So you have to do state management. And the other reason why you have to do state management is because windows are also state, right? So you have to, so the system has to be stateful and at the same time fault tolerant in a parallel way, because it should run on thousands of nodes with good throughput and latency characteristics. And when you talk about this in a streaming sense, you need some guarantees. And the guarantees here are semantics. You know, when you do transactions, sorry, when you have isolation levels, right? Dirty read, repeatable read, serializable, and so on. When we talk about streaming, we have to give semantics like we use a record, that an event that comes in only once, exactly once, or at most once, right? At least once, exactly once, at most once. And of course, exactly once is harder to achieve because you really have to check in the case of faults. And in some cases, some weaker versions like at least once or at most once might be good enough, that could be more efficient. But Flink supports those exactly once semantics. And of course, I talked about windowing already. So the system, I'll go into through a little bit of an example of if you look under the hood. So because one of the key things here is, remember we talked about the technical efficiency and the human efficiency, and I'll go to that. There's a question.
Yeah, I was just wondering, is there a scale of data where using something like this makes sense, starts to make more sense?
Mm-hmm.
Like before that, it doesn't make sense.
Yes. So I mean, the interesting thing is there is, of course, a question: when does scale out make sense, right? Because in some cases, if you can run things on a single computer, on a single laptop in an efficient way, it doesn't make sense because there is a price for scalability to be paid because you have communication overhead and so on. And it really depends on you know, the complexity of the computation you're doing, right? If you need to scale out. For instance, if you want to run, you know, a machine learning model on every data record or something, right? Then you probably need to scale out. If the thing that you do is on even for smaller data sets already, if you are just counting them, then we know that a relational database would handle, you know, probably billions of records on a single node, right? So it really depends on the complexity of your data analysis program or query, or however you call it, right? So, and now, so what I show you here, this is a declarative, I call it declarative data analysis program. And of course, we talked about that already. Declarative is somehow in the eye of the beholder. But in this case, it's just some graph algorithm. And I think we can agree that you don't specify anything about parallelization, distribution, network communication here. So it's parallel, so it's declarative in that respect. And so what the system now does, we have an algebraic model and a cost model that enables automatic optimization, parallelization, and hardware adaptation. And it's an algebraic model and a cost model. And the important thing to point out, so this looks very much like what you would do in relational databases. So the ones of you who have taken a database technology course would know. So you have this algebraic model, which is relational algebra. You have a cost model, and then you build out of that. There's a query optimizer that is either bottom up or top down, so using either Salinger style dynamic programming, or maybe, you know, like a volcano style top down search that prunes some path, or it could even be some search algorithm like genetic algorithms or whatnot. And in the end, it comes up with a data flow graph. And this data flow graph then consists in usually relational operations, and then maps this down to physical operations like a join into a hash join or a merge join, and it decides the order of the execution and all those things. And what we do here is very similar, but quite different. And it's different because we are not talking about relational algebra here. So we are talking about an algebraic model for second order functions. And we had defined those second order functions as parallelization primitives. And we had created this model that we called, and we published it at SOC in 2010, a model that we call the packed programming model, which is essentially a set of what we call parallelization patterns that help us to reason about parallelization and then optimize. And it starts with map and reduce, right? Because as we talked about, map and reduce are parallelization patterns. So map is essentially a parallelization patterns that takes a single, input out of a collection and applies this function that independently. And I said you can parallelize that. This is what's called usually embarrassingly parallel, because you can do it at will. Reduce, because we have a tuple data model, not a key value model, but it's similar. So reduce is similar to the map reduce model in the sense you can group by a key. So it's a reduce by group. And then for this group, you handle it in parallel. But we had to extend this model in order to deal with joins and other operations that you want in the relational algebra. And the extensions there effectively are other second order functions. So you need what we would call two-dimensional second order functions, so functions that take two inputs. So the first one we need is a function, we call it cross, which is essentially taking out of two data sets the Cartesian product. So it takes one record from this set and another record from this set, and it combines them, right? And this Cartesian product, what it does is it applies the user-defined function on all combinations. So this is essentially a two-dimensional map, right? Because you're applying the user function on any combination of the two inputs. The next function you need is a two-dimensional reduce, and that function is called co-group. So it takes two inputs and it groups them by the same key, and then does the corresponding reduce on that key. So that's the second function, new function. And then
predicate is checked.
So right now there's no predicates, right? They're just applying UDFs. So the interesting thing though is you are right. So there's one very specific function, particularly for relational, that you would want for efficiency reasons. You could implement this with cross, but it's not very good. So you can do what we call a match, which essentially has an equijoin, which is now matching on a key, and based on that, applying the UDF on all matching records, right? So that's what be a match function. Yes, please.
What is the semantics of doing the cross of two infinite streams?
So the semantics of a cross over two infinite streams is indeed, so you have to do this over windows, right? So so you get the windowing aspects in here. Okay, then now the next thing is, in addition to the second order functions, remember we talked about iterations, and so we have a third order function. The third order function is a fixed point iterator. So essentially it takes the second order function expression that consists of many map reduced with many first order functions, and it's a third order function that essentially says and repeat this until a fixed point is reached. So this is essentially the additional third order operator that you need. And now the interesting thing is you can reason about those. And you can reason about this similar to how you reason in relational algebra. So we had a paper on that actually published at VLDB in 2012 that's called Opening the Black Boxes, because those user-defined functions per se are black boxes, right? But as it turns out, if I know the second order functions, then I can, with very limited technology, just a bit of static code analysis, I can actually derive a lot of things. And the static code analysis, the only thing I have to do is I have to determine for the first order function which records of the tuple, so that is which attributes it either accesses, which is a read access, so that is in the first order function, they're on the right side of an equation, or which ones it changes, which are on the left side of an equation, right? So that's static code analysis I have to do. So I can determine the read and the write set of each user-defined function of its first order function. That's the argument to a map or to a reduce or whatever, right? I can do that very easily at compilation time, and also very efficiently. And this is similar if you know, when you know transactions and data management, right? You know, read set and write set analysis for serializability as well. But here we don't do it for serializability. Here we do it for optimization, because once you have this read and write sets, you can come up with some laws of associativity, commutativity, and distributivity of, you know, the second order functions together with the associated first order function across other second order functions with the first order function, just by looking at the read and write sets. You can derive actually things like, you know, selection pushdown, even though it's not, you don't know it's a selection that you're executing, because a selection is essentially an if in the first, it's a map with an if in the first order function, right? So it's a selection. Or, you know, you can do things like a projection pushdown, because projection is essentially just taking out some tuples. So you have a smaller write set than a read set, right? But you can determine those things, and you can do those in the tree, in the query tree that you execute. So you get those associativity and commutativity and distributivity rules. You can do things like join ordering because of the cross properties of the cross and the match second order function, together with, again, the analysis of the first order function. And you can even do things like lazy grouping, early grouping, and some non-relational optimizations. So it's very powerful. And we had this paper in 2012 VLDB that describes that. So in this way, this is really how we deal with the human efficiency. So essentially bringing back what MapReduce lost with, you know, declarativity, right? And now the next thing is, of course, and that's the key, you know, a different runtime. And the runtime, in this case, it's a runtime that follows a traditional distributed systems approach of coordinator worker pattern. It has to worry about fault tolerance and resource management. It has to to monitor the continuous operations, right? Because we're having continuous queries here. It has to distribute the operators in this cloud. And back then, you know, we implemented that in Java because that was the big data times, Hadoop, Spark, everybody implementing in Scala or Java. So we're running it on JVM. But you have to do your own memory management to avoid garbage collections. You have to implement out-of-core algorithms. What happens if, you know, the data set for MapReduce doesn't fit into your memory anymore, right? You need to deal with that. And we had to worry about data stream processing, which is windowing, and also how to deal with timestamps, in particular watermarking kind of technologies and so on, with fault tolerance, and the state management. Why I want to do automatic optimization, I don't think I have to convince anyone of you, because if you know databases, you know it makes sense, right? So this here is an example now in Flink or Stratosphere, one of those query plans. It's I said it looks a bit like a data flow graph in relational algebra, so it's what the query optimizer will produce, but it's essentially a query plan of second order functions, right? You see there's a map or reduce, there's not a select or project or join. And the key thing is also I want to draw your attention to the gray boxes, which I'm not sure if you can read that, but it says something like, here it says network partition or memory local forward. So those are the communication patterns between the different nodes in the cluster. And you don't want to hand code that. So the system decides the communication patterns, the order of the boxes, and so on automatically. And this is really why it's declarative, right? It relieves you a lot from that. And back then at the time of Hadoop, and you know, even to a large degree at Spark, you would have to do that. And then the crazy thing is in Hadoop, people then started, because they realized that's not tractable, then they created on top of Hadoop systems like Hive or Pig, which were bringing back relational algebra on top of that, which was now totally strange, because now you would bring this thing back in a very rudimentary version that you just try to get rid of. And it makes more sense, I would say, to have you know, this more principled approach here. So this system reached a lot of impact. I mean, it won many awards. So best paper awards, it's, I think, pretty much every major database conference, and research highlight awards, but we also showed that we are beating the competition. And what I draw the attention to more is it really and this is why I like to tell this story. It started with 2 of my PhD students, right? So any of you can do that. So very important. So because over time, this grew into a major open source community. So here you see the exponential growth. So we started it in 2008, but here's when we started to, I think, put it on GitHub. I don't know if you use that. And then you see this is the number of actually code contributors. So not people who are using the system, but people who helped us to advance the engine over time. And now I just checked, it's more than 1,200 code contributors. And there's a vibrant community. Those numbers are all quite old. Here you can see they're probably from 2021, 2022. And the numbers for China, this here is the number of people who are meeting at meetup.com and discussing. I think the numbers of China, of course, are totally wrong because people there don't use meetup.com as a website. We just counted that as an approximation. But just to give them examples of some highly engaged users, also from some time ago. One was Alibaba that has running Flink on a 1,000 node cluster, processing millions of events per second, or King, which is an in-game analytics company in Sweden that runs it 24/7 with 30 billion events daily, maintaining states of hundreds of gigabytes. Or Bike Telco in France, who is running several Flink applications and processing 10 billion events daily. But there's lots of users, right? So in the end, eventually Google made it part of the Google Cloud Data Flow. It's on AWS, and Netflix and Uber are using it in the US, among others, and Tencent and Alibaba and many others in China, but also companies in Europe, right? So just to summarize this part, and then I'll move on, but this sets a lot of preliminaries. So this is the innovation pipeline, so how all of this started and how it became successful. And what I want to highlight here, because this is the example of how you can make university research into actually some, first of all, applied research and then also commercialize. And that is, you have this basic research, which was really the usual things. You have to get funding, you get students, and initially it was 2 PhD students of my group, then a PhD student from our distributed systems colleague joined in, then some more master students, and then we had the first initial version of a system that was running more or less well, but not so well. And then we actually started moving into more applied research. That was the time when you can get other people on board. And we started that in the context of other projects, like European projects, including the project that I mentioned with Joanna, in the context of the European Institute of Innovation and Technology, where many more people started to use some prototype version of the system. And you are really, in this case, what I call a bleeding edge customer. And bleeding because you're not just leading, you're trying something new, you're also bleeding because the system crashes and you don't know why. And then essentially you really have to help bug fixing when you work on it, right? So, but exciting times nevertheless, and because I think also in Joanna's case, people got their PhDs out of it, and great research papers came out of it, and also at KTH in Stockholm, people were involved and did a lot of great stuff. They even got some professors out of it as well. So in the end, and we published more papers, and then eventually we had a robustness level and also a community that was not just people from Berlin. That was in 2014 that we said, okay, we can donate this code now to the Apache Software Foundation. Then we published a stronger article to make even more awareness of the system. And then, however, we had to rename it, as said, into Flink. And then my students founded a company called Data Artisans in 2015. And there was more and more traction with companies using the system. So we were able to create a conference. First, we were at the typical open source conferences like O'Reilly and so on to present it. Then, because there were more and more people, we created a conference just for Flink, called Flink Forward, first in Berlin, and later on, then we were able to, through the startup, also to create a really more product-ready version of Flink, Flink 1.0 in 2016. Then Flink Forward got more traction with now having spin-offs in San Francisco and in China, in Beijing. And then since 2019, it has become an established open source system with quite some wide adoption. Interestingly, there were 2 startups that came out of it that both were sold for a significant amount of money, which also tells you the lesson. If you do something open source, you can sell the same thing twice. So the first startup was actually sold to Alibaba because Alibaba is a heavy user of Flink. And the second startup was actually sold to Concurrent, Kafka, because the engine, the streaming engine that's running Kafka is actually also Flink. And if you're interested in more fun stories about that, I can tell you more in the break. But
Volker, I wanted to ask you if you time permits. The 2014 landmark, when the project became an Apache incubator project, I mean, what was the significance of this? Because maybe also students here have their own open source projects, and maybe other people are interested in fork it, and they and I mean, was it a matter of giving it away to some structured organization that would allow it to evolve on another basis, or
well, it was about,
or could it have been otherwise as well?
Well, I think it helped at that time. So, and I think this is a discussion, great discussion we can maybe have also in the break or in the evening. But in the end, the thing is, at that time, it was a good idea because it helped you with bragging rights, right? Because that was the time when the Apache Software Foundation was big, and pretty much all the big, big data projects were Apache projects. And so you wanted to go into incubation. Incubation is a milestone because it shows that it's not just you as a crazy person having an idea, that actually some first followers that believe that your idea is not that crazy, that it actually works. That's what demonstrated that. And then what was really great is that Apache Flink, as I was told, was the fastest project at that time, maybe still is, that moved from incubation to top level projects. The top level is when you're really established, you are on the forefront of Apache. But as I said, we can talk more about that later, because I want to spend a bit of time also now, since this was really preliminary, right? This was just background. We want to start to talk about the real thing. And the real thing is the world has been changing. So the research that I do in my research group with my students is, I believe very strongly in people building systems. So we are a systems-related research group. And so the goal is to really build a system that hopefully can create those success stories. We had some other systems in the past. The most successful was Flink, of course. But we are now we always try to repeat those stories, right? And of course, it doesn't make sense just to build a system for the sake of building a system. So there has to be something new, right? There has to be some new angle on things, something that doesn't exist. And so we talked about Flink. And what's changed, in my opinion, and this is now bets, right? So the beauty about research is that you can take bets, that you project a possible future, and you think about what could be requirements in a few years. And the funny thing, by the way, with Flink, when I initially thought, hey, Flink would be used in practice, I went to companies. I'm not naming them here now, since I think we are being recorded, but we can talk about all of that offline. But those companies told me, well, nice, great project, but we don't need that. So, but that's exactly the thing about research, right? You're ahead of your time, and then suddenly, 5 years later, everybody needed it, and they all came back and said, and some were really annoyed because they could have bought it or invested in it, and they were too late because they lacked the vision back then. And of course, it doesn't mean it works all the time, but it's a good try. And now I was thinking, okay, what's changing? And there's two ways of things changing, from the top and from the bottom, right? There could be new requirements, and there could be a new hardware or a technical infrastructure that changes things, that requires a new system. And what are changing factors? And we don't know which ones are the more important ones, by the way, because in the same way with Flink, I told the key new things, except for, of course, bringing the best of two worlds, the key new things were iterations and the streaming aspect. And the interesting thing is, I thought back then iterations would be a key thing. Honestly, people didn't really care. Everybody says Flink is a streaming system, so that's really what matters here, right? So this is why you take bets, and usually take multiple bets, and maybe some work, some are not so important. And I'm telling you a couple of bets here. Some of them may be important, some not. I don't know. The time will tell. But so some requirements are, so one that I believe, and we'll go over those a bit quickly for the sake of time, is that we need to adaptively handle sensor streams. So we cannot afford, and of course Dimitris knows this in the applications that you are working on, we cannot afford to send the data all to the cloud. This is the business model of the Flinks and the Sparks and any of those systems. You send everything to the cloud. But if we have a huge sensor network with potentially millions of sensor nodes, we cannot afford to do that anymore. So that means one thing that we see, however, we will have that. We will have in the future potentially have thousands of queries on millions of heterogeneous and distributed data streams. So you have to do some computation in the fog and in the edge. And because we're talking about the fog and the edge, this thing becomes highly heterogeneous. So we have a wide range of diverse processing devices. So resource utilization for each of those devices is crucial. So you cannot do what we did in Flink or what the Sparks of the world are doing, or and of course, the Kafka is running Flink and so on. So you cannot have a JVM. So you need to actually be much more efficient with respect to exploiting the underlying hardware, because of energy considerations because of just, resource limitations. So you have to have a compiled approach as opposed to a managed runtime. We still have to look at delivery guarantees, like exactly ones, at most ones, and so on. And of course, there's an aspect of security and privacy that could include things like encryption, could also include things like limiting what data is allowed to be sent to where. Maybe, having some automated version of obfuscation. So one of my PhD students in a paper at the Sigma describing, a method for masking data in this distributed setting and automatically deriving data masks. Yes, please. Mm-hmm.
So among the problems that you faced for message distribution, did you have scenario where messages arrive out of order, like non-equal channels?
Absolutely, absolutely. And then, things like watermarking and so on, right? So there's some things that you have to, so even in Flink we have that, right? So, but of course it will be at a very different scale in this new system.
Something with a graph database where you suppose that the edge is come from different sources and they could be listed out of order, and we felt that it was hard to find application, scenario, and I was wondering if that happened. So you tell me that happened.
So we believe it happens a lot. So you see it in Flink, right? So you have so the fact that so even if it's not out of order, at the moment you start processing it, right? Because you're distributing things out to the parallel processing, and when you get it back, it might come back in a different order, right? Even if it's not out of order in the beginning, it might get out of order. So even that can happen. So, and because we are looking at state, I'm still not giving up on iterations, I must admit, because I still think they are important. But particularly also for windowing, right? We have to do with state. And state, in this case, it's really transactions. So because you have to somehow give some guarantees for the state, so that's where the transaction stream processing becomes important. At the same time, with respect to now requirement from the top, a lot of those streams that we're talking about in the world of the IoT or sensor data signals where you do digital signal processing. So we are now combining your traditional relational operations, which are filters, join, group-wise, and blah, 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 with interpolation for missing sensor values for noise reduction, filter spectral analysis, those kinds of things. And then what may or may not be relevant, but in some applications, in particular, if we talk about participatory sensing, or if you would include smartphones in this kind of environment, you might need some efficient spatial analytics, right? So that means spatial operations, maybe even indexing methods for windows and states, things like that. And another one that's very natural is, of course, complex event processing. So complex event processing means I correlate events across, so different records, right? So that means first that has to happen, then that has to happen, and that has to happen, which is, you could model some of those with joins in the relational setting, but not all of them. So effectively, you're building something like a finite state machine while you're processing. But of course, as we all know, finite state machines may have scalability problems and whatnot. So one has to see how to do this efficiently. And of course, then there's the big elephant in the machine learning. So you want to run call out some machine learning models. So the question is now, is this just a UDF call, or is this more? So far for us, this is more or less just a UDF call, but you may have to delegate it also to some specific hardware, because obviously not every sensor may be able to do that. So just to summarize this part, so the way I see the world is you have those different generations of big data platforms. So we have the first generation, it's our traditional data warehouses. Then we have the second generation, that is Hadoop, that did ETL for data warehouses or lakes. Then you have this improved program model, that's what Spark provided with in-memory performance. The fourth generation was now having streaming and bringing more declarativity back to the system and maybe iterations. Fourth generation, the fifth one is now, we don't know where it will go, but our bet is massively distributed. And now let's get more into details about this NebulaStream system. So the old view of stream processing is essentially what you have with the Flinks and the Sparks or the Kafkas. You have a workload, and the results come back, and you interact with the cloud, and the data is ingested into the cloud. Like usually maybe MQTT or some kind of format, you get it somewhere into those systems, and then you analyze it. So, but of course, if you believe Gartner, but I think even if you don't believe Gartner, there's enough information to make this reasonable, that a huge amount of data will be produced outside of the cloud, and then bringing it into the cloud is a challenge. So, and the problem of the current solution is that if you do this data ingestion, then a central messaging system that would be like Kafka is a fundamental bottleneck of those cloud-centric stream processing applications. So we did some examples here, and you see that you really have a problem with scaling with the number of producers. And So data agnostic transportation cannot efficiently reduce the amount of sent data. So, but of course, we may not even need all of that data. So that's the idea of edge computing, right? And so if we now look at this new sensor edge cloud environment, then there's a couple of things. So the first one is it's polyglot. And by polyglot, I mean the workloads become quite diverse. It's not just relational or SQL, continuous query language, not structured query language, because we are streaming. It's not that just workload alone, but it's really you call out to TensorFlow models. You may have pandas, PyTorch, right? There may be other things. And they do this, but I said maybe not in the cloud, because what you have in this environment, you have very heterogeneous compute resources. We have GPUs, we have DPUs, right, for in-network processing that you can exploit. So, you know, does anybody of you know DPUs or smart NICs? You have heard that before. So the idea there is it's a programmable device in the network, and you can actually do some data processing already during transmission, which is exactly what you want maybe to, you know, out of videos, do face detection and say, this is now a face, and everything that's not a face, I don't care about. This is an example. We showed a demo at Sigma of NebulaStream in the intensive care unit, where you have a thermal camera and you want to determine, for instance, this part of the face is getting cold, because if that's the case, it's an indication for something serious, but you don't want to constantly transmit all the video frames. So you just transmit, you know, hey, there's a cold face here now, cold cheek. Then the data I said is coming from sensors. So it's not, you know, generated in the cloud like the click streams of Alibaba or whatever. And the topology is hierarchically distributed, right? It's not just flat anymore. So you can do some in-network processing, and it is geo-distributed. However, if geo-distributed, I do not mean across the world necessarily. Geo-distributed just means you have different latency and throughput characteristics for the communication channels, right? Some of them are much slower than others and have characteristics because you might have some networks like LoRaWAN, long-range wide area networks, which, you know, are battery powered and can transmit only on demand very few items per day. The example would be if you drop sensors over forests that you know, transmit humidity and temperature to do forest fire detection, right? So, and you want to analyze it and aggregate that, you cannot constantly, you know, have those data. And then some of these devices might potentially even move. So this is now a boilerplate of what we believe is changing. And some of the things may be not important at all, some may be more important, just as in a Flink. We had those two things like iterations and streaming was in the end what was important. So maybe some of those are less important than others, but this is our vision. We're going to build a system around those pieces, and over time it will tell which ones will get more investment. Some may be dropped, may not be dropped. It depends, because it's work in progress, right? But we can, I think, agree that data processing reaches new levels of scale, distribution, and heterogeneity. And so if we look at NebulaStream at a glance, so our design goals are, we want to support thousands of diverse and concurrent queries in a massively distributed environment, which consists of millions of sources. And for the ones of you who know database systems and query optimization, this is a drastic difference. So it's drastic for several reasons. So the first one is, if you look at those query plans, I've shown you this example in Flink, right? Those boxes with the communication patterns, 20, 30, 50, maybe 100, maybe 1,000 nodes that you optimize. And you only look at one query in isolation, you run that, and you ignore the rest of the world. But if we are in this environment, we cannot do that anymore. So first and foremost, we have a topology, a physical infrastructure that consists of thousands of nodes with different communication. It's a very complex graph already of thousands of nodes. And you have to map your operations, that is the relational operations, the time series analysis, the signal processing, whatever operation you have to map them on those nodes at the right level of the hierarchy with respect to, you know, kind of resources available, and also load that comes because of other processing that those components have to do. So that means you cannot do your traditional query optimization anymore. Instead, you have to do multi-query optimization, and you have to look at it in quite a different way. And at the same time, this has to be adaptive because things change, right? So you have to continuously reevaluate, monitor, reevaluate that system, and maybe redistribute how the work is being processed. You have to do in-network processing. I talked about that already, on-demand gathering. And because we have those different and potentially small heterogeneous devices, this should run both on a Raspberry Pi and on a huge CN5 cluster, right? You have to do code generation. So you cannot have a managed runtime that just interprets things like a JVM anymore. And you have to support exactly those heterogeneous hardware. So we have published a good amount of stuff on that. So as said, so if we talk about Flink, you saw the timeline of Flink. So we did the first couple of years of research already. We had several papers at a variety of locations. I think it started in 2020 with a CIDR paper, and then moved on, our work on query compilation, that how we do this. So put some papers at Sigma 24 with DB21, and those are another CIDR, it's typo here, 23. Fault tolerance, we published at Sigma 24, query placement, DB24, and so on. But let me just give you a quick overview. And that's an analogy to, so how much time do I have, by the way? So I have 1.5 hours or 1 hour?
It was 1 hour.
1 hour 30, so that means I still have half an hour. Excellent, that's good.
35.
35, even better. And you don't have to rush that much. So,
Volker, how many people are involved in?
I'll get to that, but so in the order of 10. So, but it's a set of PhD students, master students, and postdoc, and I'll show you later. Because yes, I'm a professor. I don't do the work. I just talk about it, right? So,
That's not at all what I meant.
No, but it's there's certain truth there, right? You have the vision, but the hard work is really done by all of the students, and we'll get to that though. I have a slide on this. So, effectively, so we have this declarative polyglot language. I'll talk a bit more about what that means, but essentially you have lambdas that can call out to other languages. You have this global multi-query optimizer, which is different to Flink, and then you have this execution network that you map it to, and then what happens is you do hardware-tailored code generation within those different nodes, so that you really exploit those worker nodes that each of them running on the NebulaStream worker in the corresponding network. And of course, you have to do continuous adjustments, so the system has to monitor and over time, reallocate and evolve. So that means if you look at the workers, then the key features, of course, all the things that we said about Flink still are valid, but because it's essentially more than Flink, right? So we have to worry about this heterogeneous hardware management. We have to do on-demand data gathering, adaptive resource management. And because this is an engine where we need to support a variety of different formats, standards, and whatnot, there has to be an extensive plugin system for new data types, for new operations, right, that you would want to execute on that. So I will very quickly, nevertheless, go through application scenarios. We have gone through a couple. So the first one was, that was really more or less a demo, exactly a demo. So it was a simulation, it was not real. An Internet of Things application where we looked at a smart city that consisted of a couple of sensors. And we demonstrated that at VLDB in 23, I think, when VLDB was in Vancouver. So running on a Raspberry Pi, having some simulations and running on a couple of Raspberry Pis as the smart city environment that consisted of windmills and other alternative energy sources. And also you had hospitals and energy consumers. And you could play God because we said there is no non-regenerative energies and there is no buffering. So that means you would have to react when the wind is blowing, right? So then suddenly you have to turn off lights, but you don't want to shut down the hospitals, right? So that would be all NebulaStream queries that do monitoring and then would act accordingly and maybe dim street lights or whatever, right? So that was a demo. It looks a little bit like the SimCity game. Here you can see that. You see a video of the demo. So if you're interested, I will share the slides. Excuse me, you can watch the demo. And the other demo, and I'm not sure, Yannick, maybe you're talking more about this, need me? Yeah, okay, so then I'll make this brief. So this is an intelligent co-pilot for the intensive care unit in hospitals. And the reason is, at this year's Sigma, we decided to make the system available open source. So before that, it was internal development, but we only made the single worker open source, so not the distributed setting. So there we are still working on because there's still a couple of issues that we need to fix at the right quality. There's a difference between having some student project and trying things out and making it available so that people who still are willing to suffer, but they still should be able to use it and don't suffer all the time, right? And with the distributed version, we are not there yet, but with the single worker, we are there yet. And already a single worker has a lot of benefit. And we showed an example that was a Sigma this year that won also the runner-up for the best demo award. That's an intelligent co-pilot for the intensive care unit where you have sensors like the thermal cameras, audio sources, and typical patient monitors with ECG, blood pressure, and oxygen saturation and flow of the medication. that kind of stuff, and you're trying to predict that the patient may deteriorate. And this is a collaboration with Charité, which is the largest university hospital in Europe. And they are very excited about this because what they believe this can move you from a reactive treatment in the ICU to a proactive one. Meaning when a problem happens, so typical examples after heart surgery, people are connected to a ECMO unit, which is essentially an artificial heart and lung, which you can think of as a big pump that pumps both blood and oxygen. And this pump, at some point of time, when the motor doesn't run very round, it slows down a bit, and then blood clots could form in the heart-lung machine. And at that moment, if one of those blood clots then gets back in the bloodstream, of course you get a stroke, right? And sadly, this does happen. And the interesting thing is, or the observation is, usually you would determine that, of course, with the stroke symptoms, and then the alarm sound in the ICU, and then people have to act. But you could, that's the assumption here, and there's lots of indication, detect that before it happens, because you can determine that the motor is running not quite around. You can notice that the blood pressure is slowly going down. And based on all of that, you could actually give an early warning, blood clots are about to form, which would make a huge difference. So this is the idea. So this is an example here. So we have actually this ICU bed, and then you have those signals and so on. But I think Yannick in the second part will talk more about that. You can do exactly the same thing with other machines. This is a project that we looked at with Siemens, which essentially is a paper mill. But the problem is essentially the same. So it's not, we are not trying now to predict the health of a patient, but the health of the paper machine. We want to determine will the paper tear based on 97 or so different sensors, and doing this also more or less real time so people can act. Another example was smart metering, right? So analyzing the water meter data, but those are all examples in the EU project, and the ones of you who have done EU projects know some of those are, you do it, you try it, you throw it away, right? Others are more sustainable. So some of those, that's the same here, some of them are more sustainable, some are less sustainable, but some we hope to carry further as well. So audio video surveillance, medical wearables, and motorbike tuning is a cool one. So this was a peer innovation with KTM, the KTM motorbikes, and you have sensors there about tilt, about speed, about other things, and you can analyze the quality of driving of the motorcyclist, and I can think of even competitions and several courses, right? So that's kind of a cool application, and smart manufacturing in general. But in general, if we look at use cases, so what are we looking for? So ideally something that has high velocity streams, millions of events per second, potentially even on small devices in dynamic environments that are volatile, that are heterogeneous, diverse workflows, and potentially also high demands on privacy. But I want now, would like to spend now a couple of minutes to look a little bit under the hood before we go also into some performance numbers. And of course, we'll have much more under the hood later on with Yannick. But so we have seen this picture already. So this is essentially the compilation time that is focusing on the human efficiency, and the runtime, which is about the technical efficiency, right? And if we go to that step by step, the first question is the multi-query optimizer. So that is, now you of course follow the typical way of, parsing a query, optimizing and deploying it in this heterogeneous distributed setting. Now if we expand the query optimizer, of course, you have to look at the typical steps, which is rewriting the query and standardization, like any relational optimizer would do it, or any also second order functional programming optimizer would do it if they have that knowledge. And then, however, because it's multi-query optimization, we already have things running, and we have to determine how can we put new queries into the already existing running framework. And this is very similar to what people in relational databases would do when they work with materialized views, materialized view matching. So determining effectively, I have a relational expression, and I want to determine if there's any sub-expressions of that expressions which I already have deployed for execution somewhere, right? So it's sub-expression matching. And we know that there's, of course, a lot of theory about it, also in the POTS community in particular, and a lot of it is about theory improving, which often, however, is a bit too expensive to do. So the standard boilerplate answer there is you compute some signatures, and those signatures effectively are for those parts of the queries. Which keys are you using? Which predicates have been applied? Which partitioning, which is effectively the windows, has been happening. And based on that, you can compute bit vectors, and then you can do some matching on bit vectors. And you can then identify the sharing and update the query plan. So we had a paper on that at EDBT some years ago that describes that. Then the next question, of course, how do you efficiently place the operators for millions of concurrent operations, right? So, and the interesting thing is, so there we have just so far done a very ad hoc solution. There's a lot of more research that can be done here. So we are right now, we played with a couple of placements, like we can do a top down, we can do bottom up. We also used some ILP. And I think, I'm not sure what else, did we use some dynamic programming? So we did like 4 different ones, and you can just choose, right? But of course, in the end, as it turns out, at least for now, but it's because we don't have too much, as it seems, contention for resources, then the bottom-up placement seems to be a quite effective one as a starting point, right? And what we believe in anyways, in the long term, we need to build this adaptive optimizer. You start with valid placement and you adjust over time by monitoring and measuring, right? So, and maybe then, even then, bottom up might be a good strategy. So we've implemented those 4 placements, and but there's lots of actually research that needs to be done in the space, and then in the end determine which is the best one. But we have a working solution now, but for sure not the best one. Then if we now talk about the runtime, so how do we displace in this highly dynamic environment, which really means we have to adjust, right? So because the way you can think of it, you have queries coming in and queries being removed, this Q plus and Q minus here, which are changes in the workload. At the same time, there may be changes in the infrastructure, right? New nodes, physical nodes, devices coming, or new communication channels coming, communication cell getting out of this network, so the infrastructure changes. And so the goal is to find now valid placement in reasonable time. And of course, there's a trade-off between optimization time and quality of the placement. And we are not even talking about fault tolerance and redundancy issues here, right? So this is still active amount of research that needs to be done in order to make the system robust here. Then one thing that we did so far also is how to, yes, please.
Just 2 clarification questions. When you talk about quality, you don't mean anything, like you're not even close to the notion of approximation or relevance, right, of answers. It's always like the answers are always exact.
Well, that's an interesting question. So actually, when I talk about quality, indeed, it's about the system running. So we're really worrying about building the system. Okay. But of course, we are also discussing about, when you talk about Windows in an abstract sense, right? So you will not be able to potentially maintain all data that you need in the window. So you will have to do some form of, let's call it compression, whatever that means. Compression could be just keeping a sample, then of course with statistical guarantees, and then we're talking about the quality, I think that you are talking about now. We could talk about, having some form of a synopsis, which again means, you're getting into approximate query processing. We could talk about lossy compression with just compression algorithms, right? Sometimes that, or sometimes it might be lossless, and sometimes you may be exact, sometimes you may be inexact. So far, we don't have any, so we don't have that exposed in the query language, but the important thing is the framework will support this, so one could build this. So this is why, and this is what I find so exciting about building such a system, because you can add on all those pieces of functionality. We're creating a huge playground here that people should be able in the long term to experiment with once we are ready. I mean, we're still doing baby steps, so I must say there's a couple of things that are still missing in the distributed sense in particular.
And in your previous picture, you showed that you may have Q plus, Q minus, and then you also have your nodes, right, that come in and everything. So this is your way of characterizing the fact that it's streaming. I mean, this is a bit of a naive question. I was just thinking, like, what's the difference between saying, between the awareness of streaming and the fact that you take your system at different moments in time and you just execute your queries there.
Yeah, so that's the interesting thing is, so indeed what we are saying here, you have data streaming, which is the usual thing, but you have query streaming and you even have the environment. You could say there's a stream of nodes coming and going. So there's a hardware stream that is, changes in the topology. So that's streaming too. And you have streaming in the queries because queries will come and go, even though queries are much longer lived than data, right? So data is really streaming, flying by, and either it's kept in a window or it's gone. But
and is there an awareness of the previous state? Does it matter, or is it that at a given time t0 that t whatever?
Very interesting question, and we have, and I'll get into that when we talk about research, and I talked about that with Dimitris already in our slide back. So we are looking at things like time travel, right? Meaning, can I replay my system as of, right? So this is, and you will need this. You need this for debugging purposes sometimes, but you may also need it for analytical purposes. And this requires you now to store the state again to be able to replay this window, right? And now this is an exact replay. Is it an approximate replay, right? So there's a couple of really interesting challenges. I have actually one PhD student who's looking into this, but we are starting. So one thing that so right now I'm talking about the solved things. I'll get a list of the things that are unsolved as well. And with respect to the solved things, so the hierarchical code generation, there we had, so the other challenge is essentially you have many input paradigms, right? Like UDFs in multiple languages, stream processing operators, OLAP operators. And then there's many possible compilation backends. And the goal is to find the best backend for a particular workload, in particular because we want to exploit hardware like a Raspberry Pi or so efficiently, right? And there's, of course, a trade-off between compilation time and code quality. And the way we have done that, so we have a couple of things. We have created a component which is, we call it Babelfish, which is a polyglot query compiler. And the example here is what you see here on the left is a query language, and we call it Babelfish, or it's polyglot because it speaks multiple languages, like the ones of you know, Hitchhiker Guides to the Galaxy. There's this Babelfish that can translate across multiple languages. And what you see here, you see essentially a SQL query or relational query, or SQL could also be, that calls out to a function trip profit, which is written in Python. Which is written in JavaScript. And the trip profit function itself calls a distance function that's written in Python. It comes from a Python library, which is the Haversine distance, so the distance on the globe, right? So, so that means now you actually have those three different languages that are part of that query. And the traditional answer in many systems would be, of course, you call the language runtime for the system, right? But of course, you cannot do that because if you were to call the language runtime, that would be a huge overhead if you do this per streaming for each record. So instead, you have to compile all of that together. And there's a couple of works around. The most important contribution there's really from some people from Oracle Labs, the Truffle and the Graal framework. But in essence, it's for the ones who are interested in compilers, it's called single static assignment form. So those are the technologies that you can use to do this kind of polyglot query compilation. And then you have to worry about adaptive resource management to adapt to changes in the runtime also automatically. So in particular, I'll not talk about much because this is typical if you build distributed systems, right? You do work dealing and work stealing, meaning that, I have my task queue and, whenever a worker is idle, it will take stuff from the task queue and this way we can do work stealing, that one worker takes it work away from the other because there's nothing else to do. And this, of course, has benefits. And we use this work stealing because this is key when you have non-uniform streams, if you have bursts in a stream, right? Because you have to be able to deal with bursts when some sensor suddenly produces a lot of data and normally it hasn't. And in this way, so we did some experiments on that. So NebulaStream adapts seamlessly to those fluctuating ingestion rates. And that is an important property, of course. But let's talk about some quite interesting performance, because I think this one is all just technology that it works and that we do it. But here's some performance numbers that also give an information about how to use the system or what it can do. And the first one is, so I'll be focusing here on single node performance because I said that's now the component that we have really been working on fixing. So the project has been going on since 2017 or 18, I think. But over the last year, there was a team of students, which in my group is the NebulaStream maintainer team that includes Yannick, who actually have spent a year now to make the system robust. So not writing papers, not doing research, it's really a huge engineering effort. And what you see here, this is also from a published paper called the Grizzly paper. So Grizzly is a compiler that we created that does this compilation. And Grizzly is the foundation for our NebulaStream compiler that does the compiled execution. And Saber and Lightsaber are also compiled-based approaches for streaming. So, but they're all research prototypes. So, and it's interesting to see that our work on Grizzly was really giving fantastic throughput characteristics, right? So, like Saber and Lightsaber even a bit better. But what's even more important is, comparing not research prototypes, but comparing end-to-end systems, right? Because research prototypes, they cut something short and they don't really look at the big picture and everything, right? Whereas if you talk about end-to-end systems, you have to worry about out of order and this and that, right? That sometimes the systems make simplifying assumptions. And now if we, in this case, compare, and this is an 8-core server, comparing Kafka Streams, Spark, Flink, and NebulaStream, and they note please that it's a logarithmic scale. then you can see that it's not a surprise. Flink is stronger than the original Kafka stream and also stronger than Spark, but with respect to throughput. But we beat this by essentially a factor of more than 1 order of magnitude, right? Between 1 and 2 orders of magnitude. So it's a huge difference. And at the same time, and this is also important to point out, because we do this compiled approach, you can run it on a single node on heterogeneous hardware, right? So here, for instance, you see the Raspberry Pi with 4 cores, you already achieve a throughput on this Yahoo streaming benchmark of 21.8 million records per second. And now, if I look back, what we did on the on Flink on a 8-core cluster, you can see that a Raspberry Pi for the Yahoo streaming benchmark can beat an 8-core server. So this is of course would result in huge savings, right? With respect to the overall hardware environment, as well as the energy and whatnot. So it means, what can you do with that now? So it means you can, on the one hand, with the same hardware, get better performance, or for a given ingestion rate, you can use smaller hardware, which is at less cost or maybe energy, or with the same hardware run more queries. Yes, please.
What was the result of the neon? I just wanted to do it. Can you
go back?
The previous one?
Yes.
Just to do the math. So if I bought, let's say, 15, basically 1500 Raspberry Pis, replace my Apple M1.
So now we have to be careful because this is now a single node. So that means we are, of course, scalability, is it linear or not, right?
With the money I spent on buying those,
yes,
would that make sense in the future, you think?
It might. So that's the interesting thing. So we have not tested and tried that yet, but it could very well be. That's some of the hope here, right? So this is definitely a very good potential that you could really change something drastically here. But the time will tell, but there's a lot of promise, yes. So now, as I said, it's an active project in research state. It's open source, but as I said, we have to warn you, it doesn't have the maturity or readiness of Flink or Spark or Kafka. But we are working on it. But of course, one needs others, just in the same way as, we did not, so my team in Berlin did not make Flink what it is today, right? So there was just some initial prototype, and a good amount happened then, of course, in the startups. But then also in the community as a larger, and other academics, other academic institutions, other companies did a lot. And the same might happen here. So that's our hope. But just to start, so NebulaStream, we organize it as a GitHub organization with multiple repositories, because the model that I have is in my team, you have this, and I learned that from my time in industry. So we have one master GitHub, if you wish, right? That's really the active open source code base. And then everybody who does research will get essentially their own snapshot of that, and they can work on it and do things. And if those things that they do are promising, then maybe, and if they are simple enough, also very important, simple enough, then maybe one can put them back into the actual system, right? So a lot of research that's done may never find its light in the system. Same with Flink, by the way, just because it's too complex, or it doesn't, even though it's a nice idea, it doesn't show in practice the benefits, and it would just add code complexity for nothing, right? So you have to trade those things off. But that doesn't mean it's not good for research, because you can still write great research papers and show things. And if interested, again, in the break, I can talk to you about a really cool feature that we created that never made it into Flink, that is, which is adaptive fault tolerance. And I'll be happy to talk to you about that and why it didn't make it, even though it's so cool, and we can talk about it. But those kinds of things still, it makes good research papers. So, but that being said, it's open source since Sigmod. So as a single worker, so we have a good amount of repositories, but essentially this is all students, master students, PhD students, and so on. So far out of TU Berlin, and a few collaborators from other universities, so that helped us with some demos. So this Sigmod, I forgot about that. We also had a demo of some group in Belgium that was using NebulaStream together with what's the Belgian Railway, SNCB, I think, the Belgian Railroad, and they're using it to determine, so they use old cars, and they have a small sensor that determines the braking pattern. And by determining the breaking pattern, of course, you can do things like determine, hey, this break is about to break, we need to do maintenance, but you can do other cool things. You can predict how many people are in a car because the braking pattern is quite different depending on the weight, right? And for each car, you can actually do this resolution. I thought that's quite fascinating. So things like that. And then that was done by actually a PhD student in Brussels. And yeah.
So at this stage of the project, how do you decide which pull request will be merged? And I mean, it takes a lot of effort and.
So we're very conservative. So right now, anything that helps us get the basic system going and doesn't hurt robustness, and it has to be vetted very properly. There's currently only a very small team of people that is it 5 or 6 people, Yannick? You have to help me. 6 people now that can do this. Nobody else can. And they are at the code and they guard it and watch it, and getting something by them is extremely hard. Let's put it this way, because you really have to show that you don't break anything, that it really adds a useful feature and not just something that's maybe of interest but not needed for prime time or massive. So is it a niche thing that one person needs, or is it really largely needed? But the nice thing is we have this extensibility mechanism, I should say, so that everybody can create their extensions, and those can of course be published independently. Then we wouldn't guarantee for them, but they still can be used, of course. And if a feature gets enough traction, let's say lots of people use it, but then one could actually make it part of the actual engine. So that's kind of the process. So we have in mind. We have not yet fully implemented yet because we just went open source, but that's the first collaboration scheme essentially like that. But we need to guard obviously the core very much, because any line that's added there can make things break apart for everybody, right?
So no continuous integration,
you cannot do this, I think, with the actual system, because there you need to guard it very well, because it's a crucial piece of the infrastructure. If this one breaks, right, so you cannot afford this. Yeah. But of course we use you could argue some form of a continuous integration facility. So it's now going into the next part. So we use, of course, GitHub's continuous integration facility with the pull requests, with the release process. We also have and now I would say reasonable documentation. Of course, it can always be improved, but the team spent a lot of time for the open source prime time to also document things, right? So that we have explanation. From the technological readiness level perspective, I would argue, okay, we are slowly moving into 6. So here there's 4 to 5, but I think now with the Sigma, we're probably slowly moving into level 6. And well, there's a couple of partners. I mentioned some of them already in the presentation. And we had a couple of projects already where the system was used, and some very interesting current collaborations with Brussels and the Belgian Railroad, and of course with our university hospital in the Smart ICU. And I will just, for the sake of time, since I think we are reaching the time, so here's finally the team. And of course the team is growing, and this is essentially just the it's just the PhD students and postdocs. Of course, there's also a good amount of master students involved. So NebulaStream has also grown quite a bit, right? And so it started in this case with a revamp that was really done by 4 people, and now it's 6 that are really managing the core. But we are building, and this is my model of NebulaStream, we're looking at applications, because I think that a system like NebulaStream, you will not be able to put such a system out on the market or create a startup or so around it, right? So you really have to do something for applications. In this space, it's very domain-specific applications you have to worry. But still, we want to build this generic platform and framework. And so that is why we have one team that really worries about this generic platform and framework. And this could be, then later on fed by many, potential users or startups or whatever comes out of that in certain domains. And I have said a part of my team is looking at the overall engine, and the part is looking at the application in Smart ICU. And then hopefully in the future, there will be other teams, maybe also at other universities, that look at applications in other areas. Of course, everybody who builds applications will also have to help to evolve the overall underlying system. But sometimes it's good to separate the concerns, because some people are more interested in the application development and story, and some are more in the actual systems and engine development. And then research topics that I just more or less read them. And if you are interested, we can talk more about that during the break. So there's one student who is about to graduate who looked at query optimization and deployment. I talked a bit about that already. Another student who's looking at exploiting hardware heterogeneity. That was in particular GPUs, and now we are looking at DPUs. Then fault tolerance, Anastasia's work, and Ariane is looking at CEP, complex event processing, so essentially those finite state machines, in particular how to model those with joins. And Dimitrios is looking at adaptive sensor management. He will also graduate this year relatively soon. Adrian, that's what I talked about already, is looking at this time travel aspect. So how to replay data streams. So we call this a replay operator that you have to register in advance. So essentially you can make any operation in the sensor network replayable. And you have to, however, give a guarantee for replayability. So and that's where, getting back to Siam's question from before, where this could be exact, but then you have to still give a memory how far you can go back, or it could be approximate, right? And then, or maybe even in a hierarchical way, like what we also know from data warehouses, also where you say, okay, the last day I'm exact, and the further I go to the past, the more imprecise I will get, right? Things like that. So we are thinking about those kinds of schemes. Xenophon is looking at operator placement and replication, will also graduate this year. Then Niels, resource efficient stream processing, Stefan, stream algebra and optimizer, and Taha is benchmarking and performance evaluation. Since what we notice is there is no real, so we always use this Yahoo streaming benchmark, but this is not really the right benchmark for this particular setting, since we're looking at a massively distributed setup in a heterogeneous environment. So one actually needs other types of benchmarks here. So, and then there is more. So we have a new generation, so like Yannick and Leonard and others that are looking at just looking into finding their specific topics in that space. So with that, I will go skip through those because those are just more details on those topics and conclude. Well, I've shown you the slide already, but the key thing is to summarize. So what we are trying to do is to build a system with thousands of concurrent queries in a massively distributed environment with millions of heterogeneous sensors. And our technologies that we're currently seeing that really make a difference that we have to implement and are actively working on is adaptive resource management, on-demand gathering, in network processing, code generation, hardware, heterogeneous hardware support. But there's, of course, lots of other things, right? So if you drive down, and that's the beauty when you build such a system, so you discover lots of exciting research challenges all over. And with that, I'll summarize. So it's really a general purpose end-to-end open source data management system for the, you could say the IoT, but for massively heterogeneous distributed environment we're trying to build. And if you're interested, please join us and collaborate. So on the one hand, we are always looking for people who are willing to try out the system, who have a certain degree of willingness to run into trouble. And but we are very interested to learn about problems. At the same time, we are also hoping that people will come and maybe help us fix problems, right? Because of course, one only can scale with the number of people to a certain degree. At the same time, we are also hiring. So that is, if somebody now is interested, particularly tenure track postdoc positions, if somebody is graduating PhD and is interested in this topic, distributed systems, has a systems background, really wants to build systems, has experience. And we also have some PhD student positions in our graduate school, of course, available. But in general, I think it's a large playground, not just in Berlin. The goal is now that we want to grow this in the same way as we have been able to grow Apache Flink. And with that, I thank you very much for your attention, and any questions either now or in the coffee break or in the evening. Thank you. And of course, we will hear more about it from Yannick, where you'll get a bit more of a hands-on experience, what it means to play with the system.
Yeah. Do you have any questions, Professor?
Yeah, the maintenance and making sure that, I mean, is there like a main engineer or a bunch of main engineers that kind of do this job of making sure that things are smooth?
I mean, define main engineer. So essentially what we have is I have 6 PhD students and I have 1 tenured postdoctoral researcher, or postdoctoral is not quite hitting it right. So it's, you probably would say a reader or a lecturer in the UK system. And who is really having this as, on his agenda as a key person that's more kind of overseeing it
for a longer period of time.
So that person is around for a longer period, and at the same time, of course, still, I mean, it only will work if the PhD students stick to it after the PhD. So that's why hopefully, some of them may be interested eventually to create a startup or apply it in a certain way. So this is how those things, or if others take it out, right? So the crazy thing is, are we still recorded or are we off?
No, we can stop. Hold on, just a second. Just a second. Yeah, you're right. Just a second.
Because if we're off, then I will tell a couple. Will be happy to tell a couple of things that I would not tell on camera.
Yeah, doing it right there.
But I will not tell the baby in the broad. I'm sorry about that.
We
But
can
you can catch me on that.
Yeah. Well, I will anyway send you those videos so that you can.
Yeah, I think everything I said is okay. That's good.
So welcome back to the second hands-on session by Yannick Schröder, TU Berlin. He is a PhD student and also a maintainer of the NebulaStream stack, and he will present a tutorial hands-on on the development. Welcome, Yannick.
Thank you. Yes, so I'm happy to be here and give this tutorial, like building on the foundations that Professor Markel talked about how the system was like designed and what gap it wants to fill, and I will like build up on that and give like a more practical insight how you could use it for your research, extend it for your research, and also like deploy your own processing pipelines, giving like an example that is derived from the Sigma demo, and then building upon that step by step, basically taking the steps the team did to arrive at the result that we did. So yeah, to recap the previous presentation, there were some talk about the foundations and where we come from and the goals of the system, and yeah, this gives like the context and the foundations for this deep dive. So I am, yeah, as introduced before, like one of the maintainers of NebulaStream, and I just started 9 months ago, so I'm not there for a long time. I started 9 months ago as a PhD student at Volk Markets Group, and I was part of the ongoing refactoring of the system that took place last year, and my focus was efficient I/O and networking of the system to really like support the goal of millions of sources at the same time. You need like very efficient a networking stack for that. Investigating stuff like asynchronous I/O, and now currently I'm working on the distributed part of NebulaStream, like basically executing queries over these sets of nodes in a distributed topology. And my research interests are a bit different. So time series analysis is something I've worked on in the past, and I want to integrate into the system. One specific part of that would be like the alignment of lots of different sensor streams that may have different sample rates, and to really align them together so you can feed them, for example, into one machine learning model. And in general, I'm passionate about like just declarative abstractions and using them to get the most performance out of the system like this. And I would just, I think, yeah, skip mostly about this as Professor Marker has already talked about it. Like one major thing that I should touch on here is that the system is written in C++. And the reason for that is that if you are like really targeting these low-end devices and work in this resource constraint environments, you don't really want to work with a JVM or Python because this just adds too much overhead. You cannot run these queries with the overhead that you have in those languages. So you really need a compiled language and a systems language. And yeah, so we have currently, we're writing some parts of the distributed networking in Rust, and add this into the system. I know lots of people are excited about Rust, and it works together with C++ in an okay way. Yes, so the main thing that was done in the last year, or that was the focus of this refactoring, was to make the system extensible and adaptable. And this is also what a large part of this tutorial will be about, how you can use the stuff that we've done to extend it and make it your own and do your research with the system. So yeah, so as we talked about, we are now open source since I think since 2 weeks, and the focus was before to really improve the stability and testing, because in the end, having like a good CI/CD and really have a lot of tests, a test suite that has like a good code coverage basically is very important to also improve downstream productivity, because when something fails and you don't know why all the time, then it's not really possible to iterate quickly and get your stuff done. So these foundations are really important. The robustness is what we've called it, and also the extensibility, so it gets to be a really good research system. And the next like major steps are distributed and also the query optimizer. Yeah, and I'm one of 6 maintainers, and yeah, some of them have been there for a longer time. I've just started, so maybe I don't know everything, but if you have any questions, just interrupt when I'm talking. So 2 weeks ago, there was a SIGMOD conference in Berlin, and the team presented this smart monitoring system called NeedMe. And so the focus there was really multimodal data. So you have an intensive care unit bed, and you have some sensors attached to it. For example, lab values, some other sensors like blood pressure, heart rate, and also a microphone. So you have audio input and video. So a thermal camera and an RGB camera input stream. And the idea was to really combine the data together and yeah, have a smart monitoring. And when something occurs that is out of the ordinary, like basically and normally you generate alerts and similar. Yeah, and the idea is that this would then help, like for example, doctors and people working in the hospital to focus more on other things. Yeah. So one part of this was audio processing, and so the thing about audio is there's like really high frequency. So for example, 16 kilohertz up to like 48 kilohertz. So lots of samples coming in each second. And so for this kind of load, it's really beneficial to process the data at the edge. For example, that's also what we've heard about in the last talk. You don't really want to send this to the cloud because just the round trip time is so long that when the patient cries for help, it might already be too late. So yeah, that was one part. Another part was video. So video data isn't as high frequency. For example, here there was a thermal camera that has 9 hertz and an RGB camera with 15 hertz. So 15 frames per second. But of course, like each of these frames is larger in size, so you still have substantial data volume. And yeah, in the demo, there was some like face detection, and from the heat map and like you can like get the temperature in specific parts of the body, and then combine this maybe also with other sensor data and generate alerts. Or here is something out of the ordinary, like the temperature in a specific part is too high or too low. And then for these changes, you can generate alerts in real time. And another thing could be like this pattern specification that's called like also complex event processing, where you can define specific patterns that you want to detect in the stream. And this might be easier for some people that don't know like SQL to encode their domain-specific needs, and then we can like compile this into a query and process, and maybe when we detect that this pattern occurs, also generate an alert. And while like all of these individually are already kind of solved, so for example, there's really really good audio processing or like video processing software available. The thing that is really unique here is that you, with our system, can combine all of these data streams that might be like out of sync, and then you can join them together and along the temporal dimension, like by time, and then you can detect, for example, some things that only occur when a specific state is reached in the different modalities. So, for example, something happens in the RGB or in the thermal camera, and something suspicious, something happens in the microphone, like in the audio input stream, and those things individually might be okay, but combined together, there might be a problem. So this you only get like from combining all of these together and have this multi-modality in the system. So this is something that's different. And so this, all of this setup with the ICU bed then can be encoded as this kind of large query plan where we have like the different sources, the video source and the audio source and some laboratory values. And then you define windows on this data. So you group data in like every, I think here's 250 milliseconds, and chunk it together, and then do some aggregations and joins. And then when some values occur very often, you can generate these alerts and react on them. And so what I want to do in this tutorial is go over like a couple of steps that might help you interact with the system and use the system, and teach you or like empower you to really experiment with the system. And first we will take a look at the system level tests, which are a nice entry point. Then we go to how to deploy, so how we can really have a production deployment of NebulaStream. Then I will want to show you the extension points, so really what kind of components you can extend and what is possible. And lastly, we recreate a small like speech recognition model inference, and show you what kind of stuff you would need to do to quickly like get a query going that does speech recognition for you in a real-time scenario. So yeah, of course, yeah.
If everything is running on the edge in Needme?
I think so. Yeah, I think it was one node, one worker where every data stream was fed into.
So we had one Raspberry Pi, I think, right?
Yes.
The challenge is, yes. I think at some time it was getting quite warm, right?
I also had this question about the platform. It was not mentioned because usually it takes a lot of time to instrument it. And why not smartphones? Because smartphones are already equipped with all the cameras, all the thermal cameras, it has a Linux operating system, it's all the hardware. It's like has massive CPUs compared to Raspberries that run hot.
Yes.
So I mean, it's a matter of the equipment in the ICU, right? So but I said this is just an example that's possible. So what in the end would be deployed in an ICU, of course, would be a decision of Charité, right? But to be honest with you, I'm not sure if they would use smartphones. I don't think so. So I would imagine that obviously there's some medical devices, with certain medical device probably certifications or whatnot that they would use. But in the end, for us, it doesn't matter, right? So it could be smartphones, but but what we want to show here is in particular the integration, and
we push the smartphone to its limit also for AI and computer vision. We can share experiences if you want for another project. It has limitations. You're right.
Yeah, but I guess NebulaStream runs on ARM, so it would be possible to deploy it on a smartphone.
And if not, somebody just has to do it. That's the standard answer in open source, right? So somebody can extend it.
Yes.
The issue with the smartphones is the barriers that they put with the Android Studio. That is the issue. While using, for example, Arduino or something similar, and give you the availability to do whatever you want.
You mean they place high barriers to install software?
They allow you to do something there with the smartphone to not destroy the system.
Yeah.
Also, TensorFlow, I remember during my bachelor thesis from this university, they create with the SparkFun an Arduino special for AI, for audio recognition and object detection.
Yeah.
Yeah. No, and as I said, all of those features, and of course, you could deploy that, and you could compile down NebulaStream and use that, right? So conceptually, nothing is preventing it from doing that. The question is only, when does it make sense and when not? And I think there's decisions, right? Some are technological, some are more organizational. There's many factors and barriers potentially, but I would suggest maybe just continue, because the idea is here to show you how you could use it, right? And of course, you could do this in a smartphone. And of course, you could do this on a GPU cluster. In the end, it doesn't matter.
Can you use it in a Windows machine or just Linux machine?
No, only OS we support is Linux. You can run it in Docker. And yeah, so we support currently, I think, ARM and x64 CPU architectures, but only Linux for an OS. If you use Windows, you would need to run it in Docker currently. Okay, so let's start with system level tests. And so there was, so as part of the work we've done in the last year, one major focus was to focus more on system level tests as opposed to unit tests, because they have several advantages. For example, they serve as really good documentation for users. So when you have a large suite of system level tests where you define queries and then the expected results and you test that, it's also really helpful for people to see what's possible in the system and to get to know the query syntax, basically. And also, of course, it tests the entire system. So it's not like specific part of the system, but you really test a large portion of the system. And yeah, also way easier to reason about, and it's always a bit annoying to mock all your dependencies when you write unit tests. So this is our system level test interface. And so it's really easy, and you can even run it as a plugin in CLion. So in the IDE, you can just click on it with a button and then start it. And you can also debug it just by clicking on the beat. And so up in the top, you can see the just small header describing what the test is about. Then you have a definition of the source. So data sources are like describing where the data is coming from and how it looks like. And then here, for example, you define a source called audio source, and then you define the schema of the data, which is timestamp and the value. And then you say you want to define the data in line, so right below. So then you just enumerate your testing input, and then you define the sink. So this is where you place your results, or where the system will place the results. And there you also give it a name and the types or the schema that will be the result of the query. Then as the third step, you will define the query. So we have kind of a SQL-like syntax, so a SQL dialect with some extensions like for stream processing. And this query is just like reading the data from the source and writing it into the sink. So it's basically acting as a glorified message broker. And then you have a separator, and at the end, the expected result. And also I can just show you a system level test here. I think maybe use this one. So here we have in our repository, we have our, I think it's large enough, right? Probably. We have different groups of tests. We have benchmark tests that use large data, and also for different operators. And I think it's here. And we have, for example, for the map operator that just does a transformation of a tuple, we have several tests. And this is the syntax that I've just told you. You have the source and you have the data, couple of things, and then here we have different queries that test maybe different functions. For example, here we're just adding one to the ID, and then we can start this just with the button. It's weird that it needs to build now. So it doesn't build anything. So yes. Now you can see the test passed, and if you have, if you like, do some stuff and maybe you pass in the wrong result, or the system doesn't work, what you've written, then you will get a really nice like message what's the problem actually was and what part was missing, and then you can build on that, and you can even debug this test. So you can run in interpreter mode and then debug this specific test, and then see what went wrong. So yeah, this is our system level test interface, which where a lot of effort went in, and I think we have like at least 100 of these system level tests now.
What do you mean by system?
You test the whole system. So you submit a query to the system, and then you tell it what the result should look like. And then after the system is done processing, you get a result back, and then you just compare it. And then if it's wrong, the test fails, and if it's correct, the test passes. So it's basically you test entire queries. And so now let's move to deployment. And so for deployment, we give the system a query description, and there are like also multiple parts to that. Currently, there's a YAML interface, so you can define a YAML file and pass that either with file path or directly and with standard into the coordinator. So at the top, we have a query that we want to execute. Then we define the sink, so where the data should be placed in the end. You define the sink, give it a name and a configuration. For example, here, it should be a file sync. So we want to write the results to a file, and we want to have a CSV format. So we want comma separated values. And yeah, and then we of course need to specify a path. And then we have, as the last two steps, we have the concept of logical and physical sources. So a logical source just defines like abstractly what to read. And we also have an identifier here, we call it audio stream. And then we define a schema, so how the data should look like. Then we have a 1 to n mapping from one logical source to potentially n physical sources. And a physical source is basically an instance of a logical source. So it refers to a logical source. So all of the physical sources have the schema that we specified here, but it additionally describes the input format. So the format could be differently. So we could read or we could read data with the same schema, one from a JSON input and one from a CSV input, for example. And then we specify the type of source, so where we want to read this data from. And an example would be a file, another TCP stream, UDP, some like serial port interface, MQTT, Kafka. There's lots of possibilities. And as long as these different data streams have the same schema, you can use them and like have all of them point to one logical source. Yeah. And kind of also like this get parallelism for sources.
About the data types, because you start out with binary data, but you end up with character data. Where in the middle does the transformation happen? Because
in the sink you have a config, and it says format CSV. So right before the output, there will be a transformation where the bytes of the like internal format will be encoded into the text.
But everything is binary in the pipeline.
Yes. Within the pipeline, everything is like in memory C++ objects or structs, and then you can format it to be like a human readable form, like JSON, XML, and CSV, for example. So yeah, maybe. Okay. So let's now talk about the query lifecycle. So now that we've defined a query, we can give this YAML file to one of two executables that we have in the system. And the first one is the coordinator. And this coordinator basically receives the queries from the user and does a sequence of transformations to transform it. And the first one is a parser. There we like transform the SQL query into a tree, into a logical plan. Then we have a binder that looks, are all the names of the sinks and sources correct, and do we have them in our catalog? Do we have them defined? And then we have a global optimizer, and this one will just like apply a sequence of phases where it transforms this logical plan to another logical plan that's hopefully better. And as a last step is something that we've recently like worked on for distributed. It's called Decomposer, where you then split the query plan. So the logical query plan, you split it and send the different partitions or fragments of this plan to different worker nodes so that they can execute it in a distributed fashion. And yes, so this will be done via gRPC. So we have a gRPC client and this coordinator, and this will then send the prepared query plan fragment for each of the nodes to the nodes where they are then executed. So this could be then multiple workers. So for example, this left part of the plan could be sent to this worker here, and then the other parts could be sent to other workers. And the placement, like where these different operators go, this is part of the optimizer. So there will be like maybe different strategies like bottom up placement, like placing from the edge to the cloud, or like in reverse. And then you just have these fragments and you send them to the different workers where they will be executed. And so there we have a gRPC server that's waiting for incoming plan fragments. And then we have a process called lowering, where the logical plan is then like undergoes a sequence of intermediate representations that lower the plan to an executable plan. So basically, in the end, we have machine code. So the last step will be the compiler that we've also talked about, or that Professor Marke talked about, where we have one component or library that generates machine code for this specific query at hand. And so this will be split. So the logical plan will be split into pipelines. So one part would be the source. Then there would be, for example, in this join we have here, there would be a join build and a join probe. And in the end, we have a pipeline that's the sink, and these are invoked in sequence. And the pipelines that really benefit from compilation, so where we have where we know a certain schema or have certain information about the plan, we generate this machine code for these pipelines, and then the pipelines are invoked by the runtime that you can see here on the right. So for example, we have a buffer manager that manages the memory, a query engine that manages the execution resources and invokes these pipelines on worker threads. We have a source runtime that will like drive the sources, have the sources progress and ingest data into the system. And finally, the sink, and the network channel will handle all the distributed coordination and the sending intermediate results to other nodes that continue processing. And I think I can. So here in the system, have the. So you can then, if you want to deploy this, you can, for example, define such a Docker compose file. And so here we have different Docker images, Docker containers that we specify. And we have these two executables. So the first one is the coordinator on the left that receives the plan. So you can invoke this with the command register. Then on what node the coordinator should run, the YAML file that you give it, and then -x to just register the query and execute it right away. And then we have the worker, and the worker just starts and keeps on running and waits for query requests. And yeah, this is a generator that we use for this demo. And this generator is a TCP server that is attached to the microphone of my laptop. So the microphone will listen for audio input and then write this audio stream into a TCP socket. And then we in our worker will have a TCP source that reads this audio stream and processes it. So yeah. And
have you built encryption inside the communication or not yet?
I mean, no, I think the TCP source that we currently have is just a raw TCP stream, but this is one thing that is very easy to add now. Yes. You could just define a TSL source that uses an encrypted TCP stream, and then this wouldn't be that much work, I would. But it's just, yeah, one of the examples where you could extend now the system. And so now we want to move to a bit more exciting part where we start now extending the system and build our speech recognition pipeline. And so the common scenario as a researcher could be like your mentor has a cool idea for a demo and wants to detect some words with ML. So we could just use some ML pipeline and detect words from an audio stream, from a microphone. And the problem is that, of course, audio processing isn't really typical relational workload. And also machine learning is not typically included in like stream processing systems or databases. So we can now really figure it out with the extensibility that we have now, if we can build such a pipeline of speech recognition into a kind of a stream processing system that we have. And yes, so this is the pipeline that we want to build. So on the left, we have an audio stream, and then we want to recognize what words have been said at specific points in time. And if there is some word that we say is an important word, maybe it indicates a critical state of a patient, then we want to generate an alert in this case. And so in order to now do this and build this pipeline, we first look into what extension points we have in NebulaStream. So what kind of components we can use and extend to implement this. And this is an image that we've already seen. This is the architecture of the worker. And so the data flow is from left to right. So the worker receives these queries and they go through the compiler. So we have the machine code for the different queries in the pipelines. And the data gets streamed in by the external systems you can see on the left. And the boundary between the external system and NebulaStream, this is called the sources or source connectors. And the task of the sources is to get the data into the system. And then what follows is called the input formatter. So maybe the data comes from a CSV file. So we don't want to work with comma separated values and text encoded values in the system because it's really inefficient. So this is the task of the formatter. This takes text encoded data, for example, and turns it into our native in-memory representation. And then we have the query engine where the really like the main query is executed. So the pipelines that comprise the plan. And then we have the reverse on the other end. So if we are finished, we can optionally write it to a different format again, maybe the same format that we read it. And then we have the sync that does the same in reverse. So basically writes to some external system of our choice. And yeah, so we have an IO thread pool and a worker thread pool that will execute the sources, and the worker thread pool executes the pipelines. And so these are some components that can be extended or that maybe are not yet ready to be extended, and the different purposes they serve. And I don't want to go over all of them, but we've talked about the source, and this already you can extend. Same with a function. So the task of a function is to transform a field of a tuple, and yeah, for example, add a constant to it, or add two fields together. This would be a function, and you can write your own custom functions. Then something else is an operator. So it transforms an input stream into an output stream, and you can already, with a plugin system, extend an operator, and also a sync. And some of these others are currently being worked on, so they are already existing in the system, but they cannot be extended right now. Or the interface is maybe not good enough to give it out to people to expect them to implement it. So now that we have our data, so we want to work with audio data. What is audio data? Is a stream of numeric samples, and these samples represent air pressure over time. So this is what basically audio data looks like. And normally you have two things with audio data. You have the sample width and you have the sample rate. And the sample width is how many bytes you need to represent the different amplitudes. And the sample rate is how many samples of audio you have per second. So common number would be 16,000 samples, which is, I think, CD-ROM quality, and maybe more sophisticated systems use 44,000 hertz or 48,000 hertz. And so if you look at this, the audio signal as a time series, so we could attach timestamps to it and like basically divide 1 second and then give timestamps to the different samples. So then we have a pair of timestamp value, and we want that to be ingested in our system, because stream processing always, in stream processing, timestamps always are first-class citizens, because lots of these operators need to reason about time and progress. And for this reason, it's necessary that every tuple has a timestamp field, which doesn't need to be real time. It could also be just a number that increases, but there needs to be some notion of time. But the raw audio microphone data doesn't actually include a timestamp. So when I'm like speaking into the microphone and this gets sent, this is just a stream of bytes. There are no timestamps included. We need to build them on our own. So we need to attach a timestamp to each of these values. And we also need to transform the 16-bit integers that are the audio samples to convert them to floats, because our ML model will later need floats. So this is the first kind of thing we need to do. And yeah.
So I wanted to ask, is it necessary sooner or later to do some kind of local buffering? Because maybe you have intermittent network connectivity issues and you still don't want to miss the stream, in the sense like, even some audio web conferencing tool uses, you are disconnected, then it speaks faster just to communicate the initial speech without losing. But will this be a requirement eventually, or if you are lost, if you don't have connection, you completely disregard whatever was transmitted in the pipeline?
Depends a bit on what kind of external system you have. So with TCP, what the protocol gives you is reliable transmission. So the data will be buffered on the sender side, and it will be like resent. But there are, of course, some systems where you cannot have this.
It will be dropped off after 5, because the queue is very small. It's only like incoming request, only 5. The buffer is usually only just 5 connections, and you start getting TCP drop-offs.
Yes, so I think so in distributed computation, so like when we're sending data in between nodes, there will be buffering, but from like external systems that are not able to, like Kafka, store the data like endlessly, there will be currently loss of data at some point. Yeah, but as long as like you use reliable transmission as a source, then it should work, as long as it doesn't, like the connection isn't lost for too long of a time. Then I think this would be a problem in any system. So let's just talk briefly into sources, because we want to now implement our own custom source that reads data from the TCP stream and attaches timestamps, because we need those timestamps for the rest of the pipeline. And so the simple task of sources is to just write code that ingests data from your target system into a buffer memory. So we provide the buffer, the buffer allocation, the buffer metadata, and the life cycle. So when this source is started and stopped and invoked, this is all done by the runtime. And the only thing that you need to do when you extend the system by building a source is to write the code that fills this buffer, basically. And there you have you need to remember where you are in your buffer and how large it is, and then you just return from the function when the buffer is full, basically. And so yeah, this is what I just talked about, why we want to have this custom audio source. And this is how the interface of the source looks like. Basically just 3 functions. You have a function open, which sets up some resources that you may need. For example, it opens the connection. You connect to a TCP server or MQTT or Kafka, or open a file descriptor. And then we have the close method, which is the counterpart of the open method, and that's basically just shuts down the connection. And between that, we have potentially infinite number of calls to this fill tuple buffer method. And there you receive a reference to a tuple buffer, and then you just invoke whatever API you're using or what library you're using to fill this buffer. And if you're done, you just return from the function. And you can treat each buffer basically as a blank sheet. So you can you can be sure that that you can start writing from the beginning, basically. And so maybe now I can show a bit of code. So, and this is now really large, but this is this. Remove this. This is this fill buffer method, and here we calculate how many how far we need to increase the timestamp after each tuple. So we just divide a 1 second in nanoseconds by our sample rate. And here we fill the buffer. So we call the TCP API to just fill the buffer. Before that, we calculate how many samples this buffer can hold, because when the audio samples are 16-bit wide, we want to transform this into an 8-byte timestamp and a 4-byte float. So we basically increase the amount of data that we have. So we need to calculate upfront how much data this buffer can hold and only read that much data. And then we apply this transformation where we, and this is defined here, where we just write this this index, and this is our timestamp. So it's not a real timestamp, but just an increasing number in the correct interval. And yeah, then we copy the result into the buffer, set how many tuples we've inserted, and increase the pointer to what we've written. And of course, this needs to be different for different sample widths. And then at the end, we just return how many tuples we've received. And yeah, this is an example that these are just like 50 lines of code. And this now like enhances the TCP source to convert the values into floats and attach timestamps to each sample. And so now I can show you if this works now, and show you the this query here that we've seen earlier, where we just have a select star from audio stream into file sync. And then after we've recorded some audio data, we can just play it back so that we see it worked. And so here I can just do this. And I think I need to go here because the microphone is here. And now I can speak into this. And yeah, I hope that you can hear something because after 15 seconds, this shuts down and plays back. It's stopping now. It's maybe quiet. Microphone is here. Yeah, I mean, and now I can speak into this. Yeah, I hope that.
So that's a pattern effect actually.
So the quality is really bad because the microphone uses a sample rate of 48,000 hertz, but the model later expects 16,000 hertz, and the downsampling I use is really bad. So the implementation of the downsampling is just take every third sample. And when you want good audio quality, you need to like apply some filtering and smoothing. So yeah, this is why the quality wasn't as good, but it works. So the we can like insert like stream audio data and then put it into a file and then play it back later. So the audio source works. And
so is the 16K a library limitation, or is it just bringing too much processing to your stack?
The 16K is like just a model that we use for the speech recognition, just expects an input size of like a tensor of 16,000 samples. You could also say you use 48,000 hertz and then have like a third of a second streamed into the system, but we want later a window size of 1 second, so that's why we do this. Now, the internet is broken.
To which network are you connected to?
My hotspot, because the Wi-Fi isn't working for me. And I can also try to open the login page.
Yeah, do one login again. Maybe it's Cisco Smartness System.
Maybe when I have.
Yes, you are now in. You have to refresh it, I think, every once in a while.
Okay. So yeah, we have our source set up. So the next part would be model inference. So we for the NeedMe demo at Sigmod, we integrated a model inference operator, or re-added, and the syntax we want to have is basically this select infer model and then give it an input stream and a model. And we define this model also like in the YAML description, give it a file path to where the model's parameters are stored. And then we can use this infer model syntax to invoke the model with our data. And so the thing about this model is that it's stateless. So it doesn't batch the data up for you and then invoke the model with a correct input shape, but rather expects you from the outside to give it a tensor of the correct size. And this is a problem. So the model expects 16,000 audio samples and then returns 32, so probability distribution of 32 possible words that it was trained to recognize. So it can recognize 32 different words. And so in order to give it the correct number of samples, we need some way to group together these values. And it did basically discretize the stream into these chunks of 16K audio samples, which at 16K sample rate would be just 1 second of audio. So we would need to group 1 second of audio and then invoke the model. So do you have an idea what kind of mechanism we would use in stream processing to group together 1 second of audio? We already talked about it also in the last presentation. The solution is not here.
What was
on the next slide. So the solution would be windowing. So you, in general, like in stream processing, whenever you want to do something with state, for example, joining or aggregating, these are like normally operations that in databases want to see or want to use all of the data until they can produce an output. And if you have an unbounded data set, like in stream processing, you cannot wait forever. So you need some means to say, okay, now we want to emit a result. And this is why we have windowing. So you define aggregations and joins over windows of data. And most of the time, or like the most common way, is to use time as a measure of the window. So you group together 1 second and then compute, for example, the average. And here we can also just use a window, but instead of computing an aggregate or joining, we can just take the values as they are and put it into the model. So we just group 16K audio samples into a blob of data and then invoke the model, the pre-trained model with this data. And so before that, I think, yeah. So what we can do to do this is implement a new custom function, and this is an aggregation function. Call it array aggregation, and it just yeah, we can use it like this. So we take 1 second of our stream. You define a tumbling window. So a tumbling window is a window where one window follows the other right away. Like the windows are non-overlapping or just disjoint, and then you combine the audio data within those windows and invoke the model. And I think how far are we? Half an hour left?
Yes. So, but for this, historic queries are not of interest, right? You're just interested in the window, because the window query is a simpler problem than the historic one. But maybe it's not useful, you know, to know that he was not breathing well like 2 hours ago. But maybe you see periodic patterns, let's say, you know, that you have this periodic coughing, and you want still to have this historic. That's why I was also asking about the local buffering. Let's say you have a time series or signal database locally, and are able to infer, you know, the current snapshots compared to the history. But
yeah, I mean, this is something, it depends on the kind of application or what you want to do, but with these kind of monitoring queries, you really want to know what's going on at the moment, because maybe all the data isn't even relevant. In some cases, it can even be wrong because you have like a concept drift. So the situation now is just different, and using old data would make it worse. But sometimes, of course, yeah, it could be interesting to incorporate all of the data you've seen ever. And then, I mean, yes, you could also like define operators that use some state of the past and, for example, match a pattern that you see now against old state. But yeah, you cannot, of course, keep years of audio data in memory. So at some point you need to say, okay, now we trigger the window is over. We cannot say we buffer 1 year. So in that case, we would need to do something different.
Of course, nothing prevents you, I mean, similar to Flink, right? Nothing prevents you to write some stream into a data address table, which is a state, right? And then of course you can refer to the state in querying, but that's just an external table. You can always combine that, right? So this is not really a significant issue because this is just some data address that you want. It's a constant table. The question that happens now is, of course, if this gets huge, so like if you have suddenly terabytes or petabytes of state, how do you manage that? So that one would be an issue, but as long as the state fits onto a single node worker.
But from audio stream, comma could have been another input source, maybe a table that emerges, you know, from an.
You mean joining?
Yeah, joining with the table that you already have from a.
I mean, yeah. So far, like stream table joins aren't in the system, but you could
have done it.
Yes, and then give it maybe a. Yes, either have a source to a database, that could be possible, like the JDBC source, and then you read from a static table from Postgres or something like this. Or you can, have load a file.
Or, which is again music for the future, but like what Adrian is working on, even refer to a replayed stream. So join with, yesterday, compared to yesterday. So you replay from yesterday, and then you can correlate today and yesterday, things like that. So far not supported, but of course conceptually yes. But there's a couple of questions: the syntax, how do the optimizers? There's a couple of interesting challenges to be done, but nothing prevents you from doing that but it needs to be added to the code base, right?
Yes. Okay, so we want to implement this array aggregation, and so in general, when talking about aggregation or how we approach this in NebulaStream, we have an aggregation decomposed into two physical operators that are in two different pipelines and invoked one after another. And so the first one is called build, so an aggregation build. And there we build up state by assigning incoming records to windows. So basically we have a window that is open right now. So we are in the middle of 1 second of audio data, and there's an audio sample coming in and it fits within that window. So it belongs to that window. So then we assign this record to this window and we build up state. And the second one is after the window is over. So we call this triggering the window because we've decided that no more events will arrive that are that are newer than the end of the window, basically. And then we can, so because this is multi-threaded and building up the state happens in multiple threads, we will combine these different states of the different threads and then into one global aggregation result, and then emit it to downstream. And this also, like this, you can also see this in how the aggregation functions are implemented. We have three functions, three methods that define an aggregation function, and they are the three different steps in how aggregations are executed. So the first is assign a record to an existing aggregation state or create one if it doesn't exist. Then the second is combine multiple aggregation states into one. For example, if we have two partial sums, we just combine them by adding them together. Or if we have a median aggregation, we have two sorted lists and do the merge part of the merge sort basically. So we just merge them together into one. And the third is emit a result from the global aggregation state. So after we've combined all the local states into one global state, we are ready to send the result downstream, and this is the third part. And so this is how this looks for such a query, like a minimum aggregation over 30 milliseconds of data. So as long as the window is open, the different threads will call the lift function, which builds up the state. And this happens in the window build operator. And then after we've triggered the window, we've decided there will be no more records belonging to that window. Then we will call the combine function, which is in charge of combining the partial states. And then last but not least, the lower function, which constructs a new record for downstream. And I think, this is how the interface looks. So we have the lift, combine, and lower. We have two more functions, but those aren't that important. And as you can see, we have the aggregation state and this record. And the task of the lift function is to apply some computation to add that record or the part of which we are interested in to this aggregation state. And the combine receives two aggregation states, and the lower receives one final global aggregation state and is in charge of sending the result downstream. And yes, so maybe we can, we have a bit of time maybe. So we have this array aggregation function. And here you can see implemented. So here we have the lift function for this array aggregation. We just get such a, we call it page vectors, just a vector, and we write the record to that because we only want to write the audio sample as it is. We're not like combining any records, we're just writing them to our state. And in the combine function, as you can see here, we get the two states. We combine them by just copying the second vector into the first vector. And in the lower function, there it happens more stuff. We don't need to go into that, but that basically constructs a new record out of all of these different audio samples that we've placed after each other and sends this one record containing 1 second of audio data downstream. And I can show you how this looks with this demo here. And here we are now seeing like in 1 second intervals audio encoded as base 64. So these are just audio samples encoded as base 64. And this is the input to the model. Obviously, it wouldn't be that nice to just see the floats or just see random numbers there. But this is now, you can see that it's happening every second. So we define this window. So every second something will be emitted. Okay. So when you look here, we can also see something called Nautilus. And this is a library that was developed by a former PhD student. And this does the query compilation. All of the code in these aggregation functions will be compiled into machine code. So none of the code that we write into these functions will be actually the code that is executed. But what we do is we wrap we wrap the relevant data into this Nautilus val wrapper types, and this then enables the Nautilus library to generate machine code through these wrapper types. And you can only place primitive types and pointers in here, but there are also one type that's called record that represents a single stream tuple, and one type that's called record buffer, and this is basically a whole buffer of tuples. So you have the record buffer and the record and the vals, and all of these enable, or all of these are types known to Nautilus, so it can trace, like before compilation, it can trace the code and generate a more efficient machine code that is then executed. So the nice thing here is, I think I've even prepared a slide for this. So the nice thing is that you can write operators and functions in imperative C++ code, and you can write it in a schema and query agnostic way, like generic code that would work for all queries. But at the time where the system has received the query, it knows the schema and it has a lot more information about how the data will look like. So it can use this information to trace the code that you have written and basically analyze it and build machine code that is tailored for just this query because it has additional information. And the nice thing is that this execution or this library allows for two modes, one interpretation mode and one compilation mode. So the interpretation mode you can use in debug build. So when you want to debug the worker, and then you can really step through the code, and the code that you wrote for the operator will be executed. But when you want the most efficient processing, you like, for example, in a release build, you can activate the compilation mode, and then Nautilus will trace your implementation and produce machine code from that is directly like generated in memory. And you don't even invoke the C++ compiler or write this to a C++ file, but directly in memory. So it's really fast as well. Yes, so this is a quick detour to compilation. Maybe because you've wondered what this Nautilus types are. So I skip over this, and so now let's see where we are. So we have like in the inner query, we have this array aggregation where we put 1 second of audio data called an audio section. And the start field is the start of each window. So second 1, second 2, second 3, and so on. And then we use this as an input stream for the outer query, which calls infer model. So it calls it with each audio section, you invoke the model, and then you get a result from this. So if we run this, I think it's a word detection. So if we run this, we get nothing that's readable. And the reason for that is that it outputs a tensor. So the type of the model, the output is just a binary data. So it's a probability distribution over the 32 words we've trained the model on. So the model was trained to identify 32 words we defined. And so the output of the model is how likely it is that this specific word is the word that has been said in that audio section. So this is not what we want. So we want to implement another function. And this time it's not an aggregation function, so it's easier. So we don't want to aggregate data together, but we just want to turn this probability distribution that we get into an argmax. So what is the index of the largest value in the probability distribution? What is the most likely word? And also the label. So then we can, from this index, we can look up what was really the word that was most likely set in that audio section. So again, in the inner query, we chunk the audio stream into windows of 1 second. Then we call the model on these chunks. And in the third part, we now invoke on this output the argmax function, which gives us the index in the probability distribution, and the model label function, which looks up from this index the correct word. So this, okay, this worked. And we see, for example, this function we can look at briefly. So here are all the words that are defined for the model that the model has been trained on. So I don't know. I think at some point we realized that the word help isn't even in the model, so it can't even contain the can't even recognize the word help. But these are the words, and then in this function we have just one method called execute, and in here we execute the input function first. So every function can have input functions, and the input function here is the argmax. So we first execute the argmax, which gives us the index, and then depending on this index, we get the correct label, which is happening here. So we return the label at the correct index. So we just index this static array here we've defined.
So what do you use for the signal processing? I mean, do you use some library for voice recognition, or is it your own code?
It's just some pre-trained model. I'm not sure what it does or like how the architecture of the model is.
It's probably not even a very good one.
No, it's not.
But I said it's just to demonstrate. So because so the goal of this demonstration is to show, obviously there is some functionality in NebulaStream, and you don't have to do any of that. You just use the SQL-like keywords and you run your queries. Yeah. But if you don't have those, because you have new data types, new functions, so you can actually extend the system to integrate those, right? And this is what's being shown here. So of course, yes. Ideally, you could use the system out of the box as is, and you don't have to do any of that. But at this stage, because I said there's a lot of still loose ends, open things, but this is the method that now can make the system grow and have now more functionality over time.
Yeah. Yes, so if we
and you could use any, you can call it to any model. So if you don't like that one, use a better one. Look at the TensorFlow library.
TensorFlow library.
It's I think it's a model from the TensorFlow library, right? Or where did you find it?
I mean, it's an ONNX model, but I think it's inside the TensorFlow model. I think this ONNX is just for using the model here. I'm actually not sure. I wasn't part of like really this inference or how this was implemented, but of course,
it's just I thought they found it. I think it's just a TensorFlow model.
TensorFlow.
And you know, if you don't like that one, use another one, right? So of course it would also be nice. So if you project this further, right? But this is a separate orthogonal problem. It would of course be nice to have a set of models available that you can call out from NebulaStream, you know, and you can maybe even navigate or browse, and it can recommend you the models that you need for a particular. But because you can obviously create lots of interfaces on top that make this even nicer and more usable in the long term, right? But we have all the basic building blocks in place so that one can do that, right? So that's the goal to show here. Yeah. Now the next thing is how do you add usability, maybe some nice GUIs, and hopefully grow in a meaningful way, but not in an ad hoc way. So because in theory now you can add any arbitrary function, right? Doesn't make sense. You click because then you create a huge set of functions that might be overlapping or relevant and so on. And that's why you can add those outside of the engine, right?
Yes.
And then, of course, if there's functions that are really important, then we can take those, make those part of the engine and the general syntax, and probably optimize even more out of them, and then play some more clever tricks. So that's kind of the idea about helping to grow a user community and advance it.
So this is actually here, this folder in the repository, Nest plugins, and this contains all of the optional plugins, like categorized by the component they belong to. So here we have some sources, some sinks, so a checksum sink, an MQTT sink. Here we have audio, a generator source that can just generate data out of nothing, MQTT, TCP, and so on. And this will contain all of the optional plugins, so all of the plugins that don't need to be in every build because they are maybe not that useful to everyone, but they are still in the repository, so they are tested. And in this CMake lists, you can just activate them. So you can just turn them on and off just with this one command. So when you're using the system, you can just decide which of these features you need and then write on or off. And then those that will not be needed will not be included in the build. So it also helps to keep build times shorter because build times are already really long. And this is the nice thing. So we have all of the plugins here, and there will be more to go in here. And there will be also external plugins that are not included in the main repository, but can make it there. So yes, so now we have our query, and if we now, I think it's the second, we now, it will output some random guess that it has. If we say like, yes, 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 I mean, it's not really doing the right thing yet. If I say nothing, it just outputs random stuff. And even if I'm speaking like the correct word, it often doesn't, because there's one problem, and this is in the way we use Windows. So if you look at this like visually as the audio stream and then how we basically discretize it, do you see a problem here that we may have with this approach?
If the words go across the window boundary, then kind of
yeah. And if you think about it, it's really likely that they are not exactly like within the boundary. Maybe you're lucky at some point, if you like cry for help enough, that it somehow fits into this 1 second slice, but most of the time it will not. So we need one small change, which is to use a sliding window. And so this has 2 changes in the query. So first we use the sliding keyword, and we additionally to defining the size, we also define an advance by, and this tells us, so every window is still 1 second in size, but we trigger it every 20 milliseconds. So we trigger it more often, and therefore we get more outputs. And now if you calculate this 1 second divided by 20 milliseconds, we can see that now every sample of audio is evaluated in 50 different windows. So the likelihood that at least some of those 1 second windows will contain a good portion, or maybe even all of the word, is increased. So this should work better now. So I don't know what, maybe I say no, 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 no. Okay, so it's already telling me no pretty often. Maybe yes, yes, yes. Also says no sometimes, but yeah, it's still not a good model, but it works better because we have like a higher probability of getting the correct portion of audio into our windows. But this then now is still not a really nice alerting system. So we can have one last step here. So we'll add one more layer. And so we have the model label, and now we can count the frequency. So we can define another window down here where we say, okay, group those results into 1 second windows again, group by the label index. So what was the prediction? And then having count greater than 20. So for example, if the model thought that in lots of cases, the word help was set, then and just then we emit a result here. So only when the count is like over this threshold, and this now goes more into an alerting system instead of just like giving random guesses of words, even when there's like no audio at all or no talking. So this we can check now. And now it should be nothing because there's just random guesses now. And if I say no, 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 okay, that's still nothing. So maybe the threshold is too high.
You didn't say it 20 times.
Yeah, no, only the model should have predicted in enough windows of 20 milliseconds. Okay. So, but I think we can go to the last one. Maybe put this down to 10. Yeah. Maybe now. Yes. 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 So now it tells me the number. Yes. 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 It doesn't filter, but it tells me it was. So I messed up something with a query. But you can see that you can build such an alerting system with just this query. I mean, it's not a small query anymore, but still, like, it's kind of impressive to now mix these kind of ML and audio processing with all kinds of relational algebra that we know from like database systems, and we can mix them together, and you can extend the system to do this for you. So this is nice. So this was the end query. So now we are at the end. I hope you're not too tired. And yeah, so what we've done is just a look at some of the more internal parts of the system. We've seen the audio source and model inference, and talked a bit about window aggregations and specifically functions that we can define. Yeah, so the cool thing is that this is now really a system that is working and that is quite robust and that you can use, but it still has like some rough edges. And of course, the reason for going open source is that you can get feedback, and as more people use the system and even contributed, now get help from the community. So it would be really helpful if maybe some of you are now interested to develop such a plugin maybe, and then give feedback and report bugs if something is broken, which is entirely possible. And yeah, it's also a possibility that you can integrate your research into the system, and contribute. And of course, star us on GitHub is also like often a very important metric. So yes, this is it. And yeah, I hope you enjoyed, and thank you.
Do you have any questions for Yannick? No?
At the end of the day, the question.
Yeah. But of course, Yannick is around, and you can ask him also questions. And